All right, everyone, you're live.
And if you can go.
Yes, I'm just sharing screen. All right, everyone, you're live.
And if you can go.
Yes, I'm just sharing screen. Everyone, you're live. Yes, I'm just sharing screen. Hello, everyone. Do you hear me well, Ramesh?
Yes, it's great. Go ahead.
Okay, perfect. Okay, welcome, everybody. This is our...
Hello, everyone. Do you hear me well, Ramesh?
You want to remove your YouTube window. Yes, it's great. Go ahead.
Okay, perfect. Okay, welcome, everybody. This is our...
Hello, everyone. Do you hear me well, Ramesh?
You want to remove your YouTube.
Yeah, it's...
Yes, it's great. Go ahead. Okay, perfect. Okay, welcome, everybody. This is our...
I think the echo is coming. Let's see.
Okay, welcome, everybody. This is our...
I think the echo is coming. Let's see. All right, sorry for the inconvenience. Yeah, I think we're set. Okay, hello, welcome everybody. This is split learning for distributed machine learning, SLDML’21. Quick announcements. This is our project website. The workshop event and schedule is over here, splitlearning.github.io/workshop.html. And we also have a Slack channel. We highly encourage everyone to join the Slack channel. It's split learning on patcheck.mit.edu/Slack. And thanks for joining. This is a very exciting event that we put together. So today's schedule is in the slide, and we start now. And we have two very exciting keynotes, one from Adam Hall by OpenMind and one by Geeta Chauhan from Facebook AI in the afternoon. And then these would be followed by a bunch of research talks in the middle. And then we have a few coffee and lunch breaks. And in the evening, towards the end of the session, we're going to have a hands-on training workshop by Abhishek Singh. And this is going to be very hands-on to be able to code your own split learning. And we're going to share different modules. And so 2 modules are today, and then the 3rd module is tomorrow. This is the agenda for tomorrow. As you see, we have a very exciting set of speakers coming up. And the workshop was put together by a bunch of really amazing people. Some of them were our alumni, some of their current students, and of course, a lot of leadership from Professor Ramesh Raskar, who leads our group. So I hand it over to Ramesh to give a quick intro and some opening remarks. Hey, Ramesh, I think you're muted. I think Ramesh is muted. Let's see. Okay, perfect.
All right. Thank you, Praneeth, for getting us started. And welcome everyone for our workshop on split learning. Let's think about how these problems of privacy preserving machine learning are becoming so critical in our life. Let's start with the classic utility versus privacy axis. On the left, we have solutions like Google Maps, where we willingly give away our GPS location to Google. And in return, we get fantastic utility. We can never get lost when we're using Google Maps, but also because of participatory contributions from all of us showing our GPS coordinates, Google can calculate if there is above normal traffic in a given area or there are slowdowns and show those reds and the greens on the Google Maps. So we can see traffic ahead of us. On the other hand, on the bottom right, if you think about health data, then the health ecosystems are very picky about using regulations and trade secrets and certain privacy rules to make sure the data is very siloed and can be seen by only a few folks. So it tries to achieve privacy, but also means that that data cannot be used for broad computation, for analysis, for machine learning, and so on. And the goal for split learning is a privacy-preserving machine learning, kind of creating this all-seeing, all-knowing system that still maintains individuals' privacy. Next slide. So if you again think about this privacy utility trade-off, on the horizontal axis, we can think about the simplest form of privacy, which is anonymization. But as you know, with overlapping data sets, anonymization, despite techniques like k-anonymity and others, are not sufficient. Other ways to protect data include obfuscation by adding noise. If you want to do a more formal way of adding noise, you might use differential privacy with certain epsilon delta guarantees. Or maybe the best way to do this is on the extreme right, which is encrypt the data. Especially if you use homomorphic encryption, then you can perform computation on encrypted data. And in homomorphic encryption, a client can get service from the server without revealing their data. Unfortunately, the server does not learn enough from the client. So depending on the application, this may be great because client can get service without revealing data. But in many cases, if you want to create kind of an all-knowing, all-seeing system that kind of raises all the boats, makes everybody get better, then a homomorphic encryption may or may not be the right solution. So that's kind of the way we think about on the privacy axis. And before I come back to the smashing aspect, on the utility axis, you might use simple statistics, aggregation, less than, greater than, histograms, and so on. Or you might do inference, saying, hey, here's a picture. Can you tell me if it's a dog, or classify the scene? But what we really want to talk about is full-fledged machine learning, being able to use the data that's siloed on client devices and still be able to make, create these global models. So two techniques have emerged in the last 3 years. One is called federated learning from Google, and we'll have speakers from the Google team, and split learning from our group at MIT. And the idea behind this new generation of techniques is how to train without exchanging raw data. So we're going to take the raw data and going to smash it into unrecognizable bits. And those bits are sent to the server, but those bits leak some wisdom about the data, but not the raw data itself. And from that leaked wisdom, the server can create a global model. And this is the technique that we're going to talk about most of today and tomorrow. So if you're coming from a cryptography background, if you're coming from a machine learning background, this is very exciting because now we can train machine learning models without access to raw data. If you're coming from a cryptography world, you say, okay, this sounds like a really good technique, but you may be disappointed because it doesn't have cryptographic proofs that the data about the server, on the clients is not being leaked. So these two communities, the machine learning community and cryptography communities, have not yet come up with a common vocabulary of what we really mean by protecting data here. So phrases like privacy and security and attacks and risks are all getting kind of confused in the way the machine learning folks talk about it and the way cryptographic folks talk about it. So hopefully we'll have time to talk about just getting the terminology right. But broadly speaking, what we're talking about today is, how do we share data from clients so that in a meaningful way, their privacy is protected. Next slide. And it's good to kind of talk about the motivation behind this. My student Utkrist, my PhD student here at MIT, and I were, participating in this festival called Kumbh Mela. It's a huge pilgrimage, 10 times bigger than Hajj. About 30 million people show up in 30 days. And we have a team of about 30 people from MIT and Harvard in India working on various digital solutions for this. And when we're thinking about various machine learning techniques, the thought struck us that in scenarios like this, especially in low and middle income countries, we're never going to get to a scenario where we can start pooling data from all the different systems without giving them some kind of a protection. And in fact, if you're not tech savvy in these low and middle income countries, they could be exploited. And this was already happening as we sat there working with many government officials and private players. And we thought, wouldn't it be great if we can actually provide these services for low and middle income countries without sucking up their raw data and invading on their privacy and regulations. And that's how the idea of split learning emerged back there 5 or 6 years ago. And the key idea for us back then was, how can we train networks so that some of the work stays on very thin clients, government machines or organizational machines, but rest of the work is done in somewhat sophisticated machines at servers. So the assumption is that you can split the work between the clients and the server. And so I and Utkrist and many others were highly inspired to work on this problem, and we worked over the several years. Let's talk about some of the techniques that have emerged. Next slide. So split learning, I like to use the analogy of kind of the elephant and the blind man, or elephant and the blind people. If you send folks with blindfold, somebody might say, hey, I have a rope that looks like it's X feet long. Or the woman might look at the texture of the wall and say, hey, the texture looks like this. Or somebody at the front might say, hey, I have, I'm touching something that feels like a snake. And if you think about it from a machine learning point of view, what these blindfolded individuals are doing is they're converting the elephant into its feature vectors. They're segmenting it and taking projections of feature vectors and then sending it to somebody. And then the person sitting in the control room might get all this information from different blind individuals and say, what you're talking about is actually an elephant, and let me provide some service for you. So in that sense, we have been able to convey something about the elephant by sending the feature vectors without the ability to create, without able to reconstruct that exact elephant. So there are two ways to think about privacy. One is identity. In this case, maybe we don't care as much about the identity of the elephant, but the second is whether you can reconstruct the original data in a meaningful way. And so in this particular case, the feature vectors of the elephants are sent in such a way that rest of it, the original data about the elephant can be reconstructed, because you can still write an algorithm to recognize and classify that this is an elephant. So split learning is kind of elephant and the blind people. Next slide. So just to make it a little bit more concrete, if you have chest X-rays at 100 hospitals, what can you do so that you can create a master algorithm to see if there's pneumonia in those chest X-rays without asking those 100 hospitals to send you, the thousands of X-rays each of them have. The way split learning would work there is it would convert each chest X-ray into a smashed wisdom. The analogy would be, if I want to build a master AI from this chest wisdom and chest X-rays, I will hire 100 medical interns, and I'll ask each of the interns to go and sit at these 100 hospitals, and they should just take notes on every patient's chest X-ray. Not the chest X-ray itself, but send me the notes on each of the patient chest X-ray, saying, hey, if there's a cloudiness on the top left and there's particular features on the bottom right, then it turns out a given chest X-ray should be treated as an X-ray with pneumonia. And all those notes can come to a central facility, and a aggregation of those notes, which is feature vectors, can allow us to create an algorithm to say, hey, if a new chest X-ray comes in, how to classify that, whether it has a pneumonia or not. Next slide. So in talking about DNNs now, this notion of smashed wisdom is to simply take those chest X-rays, run them through a deep neural network. The early layers, shown here on the top left with the green layers, execute on the client at the hospitals, and the later layers, shown in pink, execute at the server. And so every chest X-ray is converted into a feature space, which we call smashed wisdom, using the smasher early stages of the deep neural network. And then the server can do the rest of the task. The server can use it for training or for inference. Next slide. The benefit of using this kind of technique, and of course, I'm ignoring the second order details of how many epochs, how do we get conversions, how do we deal with heterogeneity, and so on. But the benefit of this kind of approach is that because the work is split between the client and the server actually is assumed to have sufficient computing power. Is you get the dramatic benefits with respect to SDG and even federated learning methods in terms of compute and accuracy and bandwidth and so on. And we'll talk about that in more detail as time goes on. Next slide. One of the big challenges in techniques like split learning or federated learning is when you send that smashed wisdom, that smashed data to the server, what is it leaking about every data point? And so this is a very important piece of research. I would say this is the most important aspect of how to make these distributed machine learning techniques robust and practical. So you'll hear a lot of presentations today about what techniques can reduce the leakage. If you use a vanilla version of split learning, it actually leaks a significant amount of information about the data points and so on. So we're going to look at this aspect most of the day today. Next slide. And then with this opening comments, I really want to invite everybody to participate in a survey paper that we plan to write about advances and challenges in split learning. As I mentioned, there are compute challenges such as, how much memory is available on clients. So if you're an IoT device, you have very little compute and very little bandwidth to communicate with the server. So a classic mindset of federated learning might be challenging because you cannot upload and download megabytes of models onto this small IoT device. What if the number of clients is very small? What if the number of clients is very large? The solutions can differ. What if some of the nodes are unreliable? The assumption in distributed machine learning is that all the nodes can be choreographed to go up and down. But what if some of them fail and fail to respond? What if some clients are actually adversarial? They're actually sending data that's just garbage, or they are colluding with another client and sending data that could. In California, you have the access to the operating system and you have access to the app itself. And you can coordinate all these operations when your phone is plugged in at night and is on Wi-Fi, they can coordinate all these operations. But what if all the entities are untrusted and there's no ownership of the whole ecosystem? And how would it work? And so we need a model that's more similar to, say, an MPEG, where one entity can compress the data and completely different entity can decompress that data. And split learning, we hope, is a methodology where one entity can convert this into a smashed representation, and some other entity can take that smashed representation and do whatever it wants with it. Then there's communication and bandwidth issues shown on the bottom left, which is if you have limited communication, then how do you deal with few rounds or unreliable rounds? Maybe not every client is going to participate in all the rounds. What if there is latency, which is one client is behind the other client? The client one may be in epoch number 37, and the second client has already finished some of that. What if there's dynamic availability because data is getting streamed or clients are in different time zones? What about data itself on the top right? Maybe some clients have very little data, other clients have a lot of data. The data can be non-IID, heterogeneous. What if a given client wants personalization? They don't want a model that's symmetric across all the clients, but they want their own personalization. How would you deal with that? What about vertical partitions? Where maybe it's health data. Some clients have a radiology data. Some clients have a pathology data for the same exact patient. How would they coordinate and create a global model? What about exposing labels? Because when you're sending this smashed representation, the labels themselves might go in the clear in a supervised learning setup. So maybe you don't want to expose the labels. Some of the techniques are like so-called a boomerang split learning, where you keep the labels and the data point together at the client, and the server only executes middle of the layers. And so the idea here is that when you say split doesn't have to be just between the layers of the DNA. The data can be split, because the data itself is split, as we talked about in vertical partitioning with radiology pathology data. The split could be because different section of the deep neural network is executing on different clients and servers. It could be split because there is an IoT device that's talking to a hub, and the hub is talking to a server. So the splits can be happening in the model space or the data space or in the environment. So that takes us to the last set of challenges, which is in machine learning, which is how do you validate that the hidden data is actually what you care about? How do you validate that the models you have trained are going to be reliable for new data that you're going to emerge? How do you make sure the data is within the distribution? How do you do parameter tuning? How do you guarantee conversions when you're not able to look at the data and the models locked away at the clients themselves? How do clients themselves trust that the smasher that's given to them is actually trustworthy and it's not going to leak the data in a significant way? Because as we all know, every piece of software gets an update, and the clients have to make a decision whether I use this update or not. They don't have time to figure out if that update is going to be risky and going to leak more data. What if there is incremental updates? There are new features or new data points. Do we train everything again and ask all the clients to participate in the orchestration? And then what about invertibility, which is the most of the conversation we have today? So this is a call for researchers and partners working in various aspects of split learning or distributed machine learning to work together on a survey. We will host a breakout session next week or in coming days. If you're interested in participating, please join the Slack channel that we have and just indicate that you're interested in writing this paper together. We're very delighted about how our colleagues at Google published a paper on advances and challenges in federated learning. And our team at MIT and many others worked for quite some time together to get the paper out. And we feel there should be similar other papers for advances and challenges in distributed machine learning. So please join the Slack channel and let us know if you would like to participate in this, in writing this paper. And the Slack channel is listed on the website, and you should have received it in the email as well. We're also streaming this live on YouTube, so we'll post the link to the Slack channel in the YouTube chat page as well. Next slide. So let me stop there, and we have an excellent program with several keynote speakers and papers. And I'll hand it over to Praneeth.
Hey, Ramesh, thanks for this wonderful introduction and opening remarks. So we now, as Ramesh suggested, we now have our first keynote talk, excellent set of speakers from OpenMind, Adam, Tom, and Danielle.
Hi, my name is Adam Hall. I'm the Emerging Tech Lead at OpenMind. I am joined here today by my colleagues Tom Titcombe and Daniel Romanini, and it is our great privilege to speak to you today about some of the open problems that we perceive in split neural networks and some of the solutions that we propose. Specifically, what we'll be looking at is private vertically distributed dataset coordination and defenses against information leakage. The content that we'll cover with a brief introduction to OpenMind and our products. We'll then move swiftly onto split neural networks, some of these open problems, and some of our experiments around. OpenMind is an open source community of researchers, engineers, mentors, and enthusiasts, all committed to making a fairer and more prosperous world by building and teaching privacy-enhancing technologies. OpenMind is a charity hosted by a 501c3. Officially, we were declared by the UN as a public digital good last year. We also raised $1.5 million in support, and we have a global community of 11,000 members from New York to Shanghai. We have 70 researchers, 70 writers, 250 plus coders, an events team, an education team, 25 mentors, and 6 emerging technology teams: cognition, cryptography, differential privacy, federated learning, identity, and information security. Over the past 3 years, we've grown from a core group of 2 to over 11,000 members, with over 35 teams who meet week to week on projects. At OpenMind, we organize our work around 3 major public programs. These are Build, Educate, and Impact. With Build, we develop, release, and support open source software. With 86 GitHub repos authored, around 40 PRs per week, around 150 commits per week, over 300 contributors, and over 7,000 GitHub stars. Educate, we teach technologists to deploy our software. This is culminated in the creation of a privacy course, which has over 12,000 course enrollments, 15 plus paid mentors, and was jointly financed by the Oxford University Institute for the Governance of AI and the United Nations Global Working Group on Big Data. With Impact, we look to demonstrate how the world should adopt through impactful projects. Impact is largely driven by Build and Educate. However, in the next 6 months or so, we're going to release our plan for the flagship project of Impact, which will include some large-scale demonstration of privacy-enhancing technologies. So please stay tuned for that. So the first product that OpenMind released last year was Duet. This allows data scientists to conduct experiments on data owners' data without that data ever leaving the custody of the data owners themselves. So the data owner will start up a Duet session and put their data into their Duet store. The data scientists can then send their data over to the store and receive back some pointers, which they can then use to coordinate the processing of that data. When they want to return a result, it's then up to the data scientist whether or not they want to approve that request. What's really beautiful about Duet is that we can use all of the libraries which are being produced at OpenMind to extend the functionality of Duet with other privacy-enhancing technologies, like self-sovereign identity and zero-knowledge access control, or homomorphic encryption through the Tensio library, or secure multi-party computation through SciMPC. or vertically distributed federated learning. Open Grid allows a data scientist and a data owner to discover each other and advertise their data or models. Finally, we brought out our privacy course in January, and the first module is now out for free. This is Privacy and Society. Our instructors include early luminaries like Cynthia Dwork, the author of Differential Privacy, and Pascal Pallier, the author of the Pallier encryption schema. Helen Nissenbaum, the author of Contextual Integrity, which is really the thought leader for structural transparency, which we now define SIFT around. And Glenn Whale, the author of Radical Markets and Quadratic Coding. The people responsible for implementing split neural networks at OpenMind are Daniel Romanini, Pavlos Papadopoulos, Tom Titko, Tudor Saber, Abbas Ishmael, and myself. So, 2 open problems with split neural networks. First of all, we have the coordination of these remote data assets. So it might be that we can imagine a data science experiment where we're trying to learn from the inputs of one actor and the inputs of another actor, and some third actor has the labels. In order for us to be able to facilitate this use case for either inference or training, we need to be able to coordinate the data from each data actor to be concerning the same subject. We need to be able to have their lists of users and their rows the same and in the same order. That's no trivial task unless we have to share the information which we have with other computing entities. Secondly, we have the information leakage in activation signals. So when we feed data through a model and we send this activation layer to the next processor of that model, there's actually a lot of information still retained from the original data in that signal. It's been flattened, but not destroyed. So we look at some of the ways that you could abuse that and some of the potential defenses for that during inference. So I'm now going to pass you over to my colleague, Daniel Romanini, who is going to speak to you about some of our solutions around the coordination of vertically partitioned.
Is represented. Moreover, to protect privacy, it also needs a tool to be able to access the data remotely without seeing them, while still being able to do training and inference. To achieve that, we built a framework called PyVertical to do federated learning on vertically distributed data. In PyVertical, we do federated learning using multi-headed split neural networks, and I will show you an example of that in a minute. To link together the different vertically distributed samples, we use a cryptographic technique called private set intersection to reveal only the minimum required information to the different parties. Finally, to be able to allow data scientists to train neural networks on data that they cannot actually see, we implement PyVertical using PySift, developed here at OpenMind. In particular, we use Duet, which Adam presented before, to be able to connect data scientists with data owners. I will now present how PyVertical works through an example with a dual-headed split neural network. In particular, this example uses the MNIST dataset, which images have been split in halves. The data owners hold either the right or the left part of the images, and the data scientist holds the labels. To start, the data scientist defines a PyTorch split neural network model of 2 segments. The first segment is pushed to both data owners, while the second segment of the model is kept by the data scientist. The second segment includes a classification layer to classify the MNIST images. During training and inference, the data owners pass to the data scientist the intermediate tensors representation from the output layer of their model segments. Finally, the data scientist concatenates those tensors and inputs them to its own model segment, and it continues the training of the inference process. Now that we have an overview of how actually the protocol works, let me explain how we assure that the data scientist combines correctly together the different data samples that are vertically distributed. To do that, we use the secure multiparty computation cryptography technique called the private set intersection. There are many variants of it, but we use one developed at OpenMind based on Diffie-Hellman key exchange and that uses Bloom filters compression. This PSI protocol works between 2 parties that have 2 sets of elements, and one of those, and only one of those, would get to know the elements that it has in common with the other party. In PyVertical, we basically run PSI simultaneously between the data scientist and each of the data owners over the data IDs. At the end of this first step, the data scientist would know which IDs he shares with each of the data owners and would compute the global intersection. The data scientist would then send this global intersection to the data owners, which would then know which kind of data to allow access to the data scientist for the upcoming computation. Note that the data owners do not get to know anything about the other owners, as they don't interact with each other directly. In this case, we assume that the data owners are honest but curious actors, and they share the data in the right order which is given by the data scientist. Of course, that could be downsides and improvement to this protocol. In general, however, the PSI protocol could be changed without actually affecting the rest of the process. There is still some work to do on PyVertical. For example, as I mentioned, the current PSI could be improved, for instance, to accommodate a multi-party PSI between all the data owners directly without having the data scientist acting as a broker. This could be useful if the data scientist does not have any data at all, and could be achieved, for instance, using homomorphic encryption. In general, we would like our framework to be flexible and support multiple configuration of vertical federated learning, but not only that. We showed an example with dual-headed split neural networks, but even though in principle split neural networks with more heads are supported, we should investigate the challenges of such a setup. Moreover, we saw an example where the split neural network segments that are pushed to the data owners are the same, but we should also investigate how the protocol and the coordination is affected with asymmetric models, but also when the datasets partition are unbalanced. Additionally, it is important that those distributed datasets and their attributes can be verified for the purpose of coordination, and this is also an area we plan to work on in the future. Finally, privacy and security of split neural networks is also a big concern. And now I will hand it over to Tom, which will tell you more about it.
Hi, I'm Tom, and I'm going to be talking to you about our research attacking split learning systems. In particular, we've been looking at model inversion attacks, which attempt to recreate the raw input data into the split learning system from some intermediate representation communicated between the parties. We look at a couple of defenses: noise defense and no-peaks, the existing work. Finally, Adam will take you through homomorphic encryption applied to split learning. The attack landscape we've been working under assumes that there are multiple data owners, each with their own private data set that they don't want to share. They convert their data into some intermediate representation using a model segment and communicate that to a single shared data scientist who completes the task. So while the data scientist is honest, they complete the task as they were expected to. They also try to recreate the raw private input data of the data owners from the activation signals. To do this, they need a trained attack model. To train the attack model, they need a data set of raw input data and activation signals. And they can get this in a number of ways. Perhaps there's a data owner who colludes with the data scientist, so provides willingly their data set. Perhaps the data scientist can just use their prior knowledge of the data set. Now, this may just be given to them. The data owners agree what we're doing MNIST, and the data scientist knows this. Or maybe that information was partially revealed carelessly to the data scientist, which they can use to train the attack model. We introduce a simple noise defense in which Laplacian noise is added to the activation signals before being communicated to the data scientist. And while this can be applied during training, it doesn't have to be. It can be applied post hoc to an already trained model. The results we show in this presentation are qualitative, but quantitatively we find similar results between applying it during training and also simply after training. The benefit of applying it on an already trained model is that the data owner can apply this unilaterally to protect their model segment. So if they don't particularly trust the other parties in the split learning system, they don't need the other parties to agree on defensive measures. They can just do it themselves. The figure on your screen shows reconstructions using the model inversion attack on a model with different scales of noise applied to the activation signals. And you can see, unsurprisingly, at a high scale of noise, the reconstructions are completely destroyed. But before that, the classes of the reconstructions are still difficult to interpret. For example, in the 4, the 6, and the 8, it's not clear exactly what they are. But the data-specific features remain. You can see the lopsided circle of the 8, for example. We compare this to no-peak, an existing work, which I'm sure you'll hear quite a bit about during the other talks of this event. No-peak trains a split learning model to both optimize the task, but also to minimize the distance correlation between the input data and the activation signals being communicated. How much you emphasize the task or the distance correlation depends on the no-peak weight of the loss. Reconstructions of the data on a no-peak system show that the class is almost always viewable, easily seen in the reconstructions. But the data-specific features are not. The reconstructions adopt a sort of generic representation of the class. And this is the opposite result to what we get with the noise. And this can be seen most notably in the 5, the 7, the 9, which become less slanted, more curved, and the squiggles, particularly of the 9, get removed. What these results show, while simple and applied only on MNIST, they do suggest that a hybrid approach is necessary to fully protect data in a split learning system. And this is just against model inversion attacks. If you want to protect against a multitude of attacks, then you'll need even more defenses. Which defense you use, no peak, the simple noise, or even something else like shredder, will depend on the particular task that you're trying to protect. Which bits of information, exactly the class or the features, for example, are you trying to protect?
One way where we can protect the information contained in activation signals at inference time is through the CKKS homomorphic encryption schema. In the example that we propose, we have a data owner with model segment 1, a data scientist with model segment 2. The data owner passes unencrypted data through the first few layers of the model, which they're in possession of. They then encrypt the activation signal output of that first segment and send this encrypted activation signal to the remote data owner, or data scientist. The data scientist can then process this encrypted data and then return the encrypted result back to either the data owner for consumption or to some third-party consumer of this inference. We define our information here as follows, where a data owner and a data scientist begin by utilizing the Aries functionality of PySift to verify certain attributes about one another using CL signatures. These can be verifiable credentials, or whether a model has been signed off by the right authority, or whether some data has been signed off by the right authority, or the provenance trail of that data, or whether it conforms to some certain schema. Secondly, the data owner and data scientist load their private data and load their model respectively. The data scientist then splits their model, sends the first half to the data owner, performs convolutional inference, while the data scientist prepares their layer for this homomorphically encrypted computation. The data owner performs inference and encrypts the activation signal that's produced under the CKKS homomorphic encryption schema. They then send this encrypted activation signal to the data scientist, who continues the computation and sends back the encrypted inference result. We define two experiments. The first experiment, the server sends all but the final layer of the model to the data owner. The data owner then computes each of these layers in plain text until an activation signal is produced, and they encrypt this under a modulus of 88 bits. This is just to accommodate a single layer of computation depth, computing this FC2 model. This gives us an encryption time of 4.6 milliseconds and a processing time of 97 milliseconds. In our second experiment, we put the split layer right in the center of the model. The data owner computes convolutional layer 1 and 2 in plain text and encrypts that signal under a modulus of 140 bits. This larger modulus is to accommodate the larger computation depth of computing FC1, the square activation, and FC2. As you can see, the size of the file is far greater than the original plain text. This is because of the extremely large key sizes used in homomorphic encryption. As you can also see, it takes over twice the time to encrypt the activation signal as in the previous example. Once this encrypted signal is sent over, it's then computed, and it takes 4.17 seconds to compute the entire encrypted layers. This is significantly longer than just computing the FC2 layer. We were able to protect activation signals at inference time using the configurations of these two experiments. Experiment 1 was a lot faster, but shared more of the model. Experiment 2 was a lot slower, but kept more of the model private. For future steps on information leakage defenses, we're going to perform an analysis of privacy of split neural network output using the shredder technique. We're going to perform an analysis of parallel split neural network noisy activation aggregation, federated split neural network. And finally, we're going to do an exploration into encrypted training of split neural networks. Finally, I'd just like to thank Tudor Sever, Abbas Ismail, Robert Sandman, Robin Rome, and Michael Ho for their contributions to PyVertical and OpenMind, and also everybody at OpenMind and all the people who continue to contribute to our community. Thank you. I'd like to open to the Q&A. Thanks.
Thanks for the wonderful talk. I think we have some Q&A on Slack, so yeah, let's keep the thread open for a bit.
Yeah, can you hear me, Praneeth?
Yeah, go ahead.
Yes, so we are doing most of the Q&A on Slack, but I will ask questions you have received for Adam. So what kind of trade-offs do you see with encryption techniques? Hello? Yeah, sorry. So question for Adam and team is, what kind of trade-off do you see with encryption techniques in comparison to noise, no-peak type of techniques for split learning? Adam, if you can unmute yourself.
Hello, can you hear me now?
Yeah, go ahead.
Okay, fantastic. Yeah, so I think the question was, what are the trade-offs between this like noise approach, the no-peak approach, and encrypted inference? So I think the blindingly obvious answer is computation time. There are severe overheads with encrypted computation, which preclude it from being used in extremely deep models where we can't accommodate for the noise that is being produced at each layer of computation. And there's also a significant overhead with using larger key sizes and doing wider computations. We haven't explored that massively just yet, but it's on our to-do list. In terms of how it would relate to looking at just like a simple noise or this no-peak defense, so I think there's like a lot of very good applications of both noise and no-peak where we couldn't apply homomorphic encryption. For example, if we want to do training, we can't do homomorphic encryption because we need to be able to update the server's model, and we can only update it using the numbers which have been created using the private key of the public key of the data owner. So there's not a way to reunify the model at the end without sharing the keys. And finally, the inference result, in this case, it's fine that the data owner consumes the inference result from their own data, but let's say this was from an insurance company, and we needed to make sure that the inference result that they received, over enough queries, they couldn't figure out who that was from or some kind of other statistical information about the data set that was used to create the model, which provides the inference. So this is an example where the noise would come in handy, or specifically Fatima Maneshkala's shredder would be really handy for reducing the noise which is shared. So thanks for the question. That was really great.
Yeah, that's fantastic. We actually have the shredder talk scheduled as well in this event. So.
Oh, fantastic! That's great.
Yeah.
Yeah, looking forward to it.
All right, perfect. Okay, so moving on with our series of research talks now. After that wonderful start with the keynote from OpenMind. So we have the first talk, parallel training of deep networks with local updates, with Michael, Luke, Seth, Mark, Badruddin, Carlo, Jessica, Peter et al. From UC Berkeley, Google Research, and GraphCore.
Hello, everybody. My name is Luke Metz, and I'm going to talking to you today about some work we've been doing on parallel training of deep networks with local updates. This has been joint work with Misha Laskin. There's a number of ways to parallelize training of deep learning models. The first and most common technique is to leverage data parallel training. The idea here is to take a batch of data and split it up across machines, and then average the gradients across each machine. Another common approach is to leverage model parallelism. The idea here is to split up computation in each layer across each different machine. Finally, an up-and-coming technique, pipeline training. Here, we take each layer and put it on a different device, and then send data through from device 1 to device 2, device 3, and so on. There are a number of limitations of the existing methods, however. The first is diminishing returns with increasing batch size. In the figure to the right, I'm showing a number of steps required to reach a certain loss value as a function of batch size. In an ideal world, we would be on this dashed line. But in practice, however, as we grow batch size, we get worse and worse scaling performance, as denoted by this shift up on this blue curve. The second limitation is networking and communication costs. As we grow the number of nodes in our cluster, communication costs can grow substantially and possibly up to n squared. Some methods can lead to underutilization of hardware. And because this hardware is often special purpose and expensive, such as GPUs, this is quite undesirable. What we explore is a family of parallelization strategies we call local parallelism. The idea here is to split up computation so each layer can be trained in parallel. To show how this works, consider training this 4-layer network. With backprop, we'd send a batch of data through the network, then backpropagate the gradient all the way back. With local methods, however, we first add auxiliary loss calculations after each layer. In our case, we use the same form as the output loss. So if we're using cross-entropy loss to some target class, we use the same thing for each layer. Next, to train this, we only compute gradients for each layer using only these auxiliary losses. And we don't ever propagate any information back through the entire net. You can see this by only showing the arrows pointing to the right between each layer. Once our network is divided in this way, we are free to spread each layer onto different machines to train. The only dependence between machines now is this forward passing of activation. From a systems perspective, local updates solve a number of existing problems with scaling. With regard to diminishing returns from batch size, local updates give another axis of parallelization. Namely, each layer, the layers themselves, can be trained in parallel. With regard to communication costs, the only information required is to send forward activations along the network. So it's much lower than, say, data parallel or model parallelism. And with regard to device utilization, each model can operate near nonstop, as we don't need to wait for any information other than forward passes from the previous layer. There's no network-wide synchronization, for example, like you would need with pipeline training. These improvements, however, come at a pretty big cost. When training in this way, the updates computed are biased. In some settings, this greedy approximation can lead to worse performance. So there are trade-offs. Before going further, I want to call out that this family of algorithm is not invented by us. Layer-wise pre-training has a really rich history, with some notable work by Bengio as early as 2007. Modern variants of the same type of algorithm have more recently been explored to train large CNNs as well as representation learning algorithms. I threw some links to a number of papers here if anyone's interested in learning more. In this work, our main focus is on scaling. To this end, we explore a large-scale study of multiple different kinds of local update methods with a focus on understanding how these methods scale with increasing compute. We also demonstrate how these methods can result in increased throughput when implemented on real hardware. There are a few kinds of local methods across groups of machines. So in this figure, we would have 3 machines running in parallel, but each layer shares a neighboring chunk. So this blue chunk is shared and this green chunk is shared. Finally, we explore chunks training. And this is similar to greedy training, but instead of backpropping each layer independently, we group layers and backprop into each of these groups. This lowers the amount of parallelization possible, but can often lead to less greedy gradient estimates and thus higher performance. The main tool we look at to understanding trade-offs between these methods are cost versus time training curves, inspired by an empirical model of large batch training. The idea here is we are free to choose what batch size and thus what hardware we can train on. In an ideal world, using more hardware for a shorter time would lead to identical costs. This corresponds to horizontal lines on this figure. In practice, however, we hit scaling issues, as we talked about earlier. This causes a slope to curve up as we increase the amount of hardware and batch sizes used. To generate these figures, we need to run a fair amount of experiments. So for a given algorithm, we try different batch sizes as well as different optimization hyperparameters, and then plot only the points on the Pareto frontier. First, we show this on training simple 8-layer CFAR10 MLPs. We show a sequence of these plots corresponding to different cutoff values, so to different loss values we're trying to achieve. On the x-axis, we have a hardware-independent measurement that represents wall clock time. This is basically the number of serial flops required to train in parallel. On the y-axis, we have a hardware-independent measurement of cost. In this case, total flops required. In each pane, we show a different cutoff value. In all these figures, we want a method to be in the bottom left. So this corresponds to low costs and training in a short amount of time. Now, depending on the cutoff value, these local methods can train dramatically faster if we're willing to pay a slight increase in cost. For example, in this 0.01 cutoff, the overlapping method can theoretically train models around 10x faster than backprop, only a modest cost increase. Finally, there's no situation on any of these plots where backprop is actually part of the Pareto frontier, suggesting that no matter where you want to be on this trade-off, using one of these local methods is desirable. Next, we look to more realistic models, a transformer trained on the LM1B dataset. Once again, depending on the cutoff value, we see large improvement in training speed in the high cost regime. So for example, here, we see quite a large improvement in wall clock time that's possible. But unlike the MLPs, however, when one does care about minimizing costs at the price of longer training times, backprop remains the most efficient algorithm. Finally, we have results on training ImageNet with ResNet 50. For this model, local updates work well when trying to achieve low accuracy values, say 50% or 60%. But when training to higher performance, we see local updates severely underperform backprop. In this highlighted pane, many of the local methods are not even on this plot, meaning that no method achieves the desired cutoff value. With this demonstration of performance gains from the previous section, we shift our attention to showing throughput on real hardware as compared to pipeline backprop. In each row, we show a different model family trained with different sized batches. In all settings, we find significant speedups over backprop. In some cases, up to 40% faster, as in the ResNet 101 case. To understand how this is possible, we visualize the execution traces for pipeline backprop using 4 chips. The red area denotes computation, and the gray boxes denote idle processors, or no computation being done. To understand what's going on here, let's first visualize a single micro batch of data flowing through this pipeline. First, we get data and run a forward pass on chip 1. This data then gets passed to each subsequent chip to perform a forward pass. And next, we perform backward passes, first on chip 4, chip 3, chip 2, chip 1. This is a single batch, however. For increased utilization, when doing pipeline training, we often run on more than one micro batch. So we can see another batch visualized here in green. As a result of this structure, there are different phases in backprop pipelining. There's this ramping up phase where data is coming into the pipeline, a ramping down phase where the last gradients are being calculated, and a steady state phase where performance is at its peak. In this case, each chip or each layer is computing a forward and backward pass. It's these different stages, in particular ramping up and ramping down, which result in poor device utilization. In local updates, however, there's no need to send data back and down, and there's no need for global synchronization. So as a result, once an initial ramp up is done, the pipeline can run at steady state for all of training, and thus result in much higher utilization. In summary, we've shown that local updates can be used to leverage more compute and thus train models faster. This comes at the cost of approximate training methods, so they might lead to subpar performance depending on the problem. Finally, We showed that they can make effective use of hardware and result in high device utilization. When working on this project, we really wanted to push the limits on the amount of parallelization that can be done to train networks. We hope that this will enable both larger models and training of models faster in the future. Thank you all for listening. I'm not sure I'll have the ability to answer questions here, but please do reach out to any of us over email and we'll be happy to discuss more or answer questions. Thanks again. Hello, everybody. My name is Luke.
Thanks for the wonderful talk, Michael and Luke and team. I just realized Luke's been answering a lot of active Q&A in the Slack channel. So if you have more questions, feel free to continue to reach out to questions to others of this talk and the previous talks. The Slack is having an active discussion going on right now. Thank you for the wonderful talk. So we keep moving with our agenda. So the next research talk is on communication efficient parallel split learning by Jihong Park and Seong and Hailin and Seong and Mehdi from Deakin University, Yonsei, and University of Oulu, Finland.
My ongoing work. Hi, this is Jihong Park, a lecturer at Deakin University in Australia. And today I'd like to share my ongoing work in collaboration with Yonsei University and the University of Oulu, which is about how to design communication efficient split learning. Here's the motivation. We are living in the era of machine learning plus X application. While pursuing machine learning plus X, we often encounter the lack of data samples at a single location. In other words, we should exchange data samples, but that is often restricted by some privacy issues and limited communication and computing resources. This motivates us to develop communication efficient and privacy preserving distributed learning frameworks. In this respect, many promising distributed learning frameworks have recently been proposed. And among them, in this talk, we focus on the communication efficiency of split learning as compared with a well-known framework, Federated learning. First, consider a parameter server communicating with multiple remotely located workers. Then, in Federated learning, both uplink and downlink payloads are the entire model parameters, and the communication interval is periodic. On the other hand, in split learning, the uplink and downlink payloads are single layer activations and the gradients, respectively, and they are exchanged for each sample. In other words, federated learning can be regarded as a shower, while the split learning is many drops. The question is whether many drops exceeds a shower or not. Interestingly, the prior works by the host of this workshop have already shown that split learning can achieve higher accuracy and faster convergence with smaller petal sizes compared to federated learning. So in terms of the accumulated bit cost until training completion, split learning is more communication efficient than federated learning. However, if you go beyond counting bits, then things are different. For instance, what about the impact of stragglers and latency? Answering this question is not trivial, particularly under intermittent connectivity, such as wireless links that are time varying. With this motivation, in this talk, we aim to ask and answer 3 key questions. Here's the first one. Can split learning control the number of stragglers? To begin with, let's recall the vanilla split learning operations. It is sequentially operated and is communicated per sample. For scalability, we consider its parallelized version, where at the worker side, data feeding is synchronous with respect to the label, and at the server side, concatenation is applied. Then the problem is that neural network architecture is not flexible, whereas communication channel quality fluctuates over time. Therefore, the server should always wait until the last straggler, whose worst case latency could become infinitely long. To fix this problem, we can add an average pooling layer aggregating all the uploaded activations, regardless of the number of uploads, Thereby, we can dynamically adjust the number of stragglers in split learning. There are several backgrounds of this. First, average pooled representations can be viewed as equally manifold mixed representation that are known to be trained as good as separate data samples. Second, based on another work to be presented as far as I remember tomorrow, we know that average pooling is effective in vertical partitioning with sample synchronous pooling. We can test the same idea for our horizontal partitioning with label synchronous pooling. And here's the result. The accuracy and convergence speed of average pooling is as good as that of concatenation as expected. In other words, pooling communication efficiency is a free lunch without compromising neither accuracy nor convergence. Next question, can split learning support periodic communication with low latency? In federated learning, workers communicate with the server at intervals of multiple local iterations. By contrast, in split learning, workers by default communicate with the server per every iteration. And fixing this issue is not a difficult problem. We can just simply increase the batch size. Here comes the background. The maximum communication data rate, which is known as channel capacity, is a well-known logarithmic function of signal-to-noise ratio. And this is achieved when the data packet length n goes to infinity. Otherwise, there exists a data rate loss term that diminishes with n. Here, the batch size increase corresponds to aggregating data packets, increasing n. Therefore, we can reduce the data rate loss when we increase the batch size. Consequently, we can observe the effectiveness of batch size increase in terms of latency, as shown in the yellow curve in the simulation figure on the left-hand side. In our simulation settings, accuracy decreases with the batch size, yielding an accuracy latency trade-off. And there are many techniques to improve accuracy under large batch sizes. So I expect one can even show a win-win strategy in the near future. Finally, the last question, can split learning handle and mitigate stragglers? To answer this question, let's suppose a straggler whose omnic transmission was failed. In split learning, this means that the weak connection between the straggling worker with the server is dropped out. Therefore, the server cannot even calculate the gradient for the straggler. A naive solution is perhaps to aggregate a non-straggling worker's gradients and enforce this average gradient to the straggler. Unfortunately, in our preliminary simulations, we observed that downloading average gradient by stragglers even decreases accuracy, particularly when the number of stragglers becomes large. To overcome such a fundamental limitation, we propose federated split distillation, in which gradient backpropagation is replaced with service output propagation. Then, by running knowledge distillation locally at the worker side, workers can infuse the server's knowledge into their models. In fact, this idea was inspired by local parallel training presented just before this talk. In local parallel training, each chunk of layers is associated with an auxiliary output layer to enable local training. Here, we can view the entire model as a teacher and one chunk as a student. Then knowledge distillation can update the student by comparing the outputs of the teacher and student. Applying this idea to split learning, the worker now has a student's output and the server has a teacher's output. Then in the forward direction, following local parallel training, both worker and server can locally update their layers. And in the backward direction, workers can download the server's output and update their local models by locally running knowledge distillation. Since this server's output always exists, even for stragglers, we can handle and mitigate stragglers. We tested this idea for a single worker with a split version of Rigid 16 model, and we validated that such an output backpropagation improves the worker's accuracy. And based on this, we are currently extending this implementation to multiple worker cases. Here's the conclusion. To improve the communication efficiency of split learning, we need to co-design split learning model architectures and communication techniques. To mention a few, we can use average pooling, increase the batch size, and propagate global output rather than gradient. I believe that this new direction of research is still in a very early stage, and we need more studies on energy footprints and privacy issues, as well as developing novel analytic tools to prove their coverages and the like. And I hope you enjoy this talk and you can come join us. Let me conclude this talk with an advertisement. Tomorrow morning, our collaborator, Yusuke Koda, will present our two wireless communication applications where we fuse RF signals and RGB camera image data through split learning. I look forward to seeing you all again tomorrow. Thank you.
Thank you for the talk. This is very exciting to see split learning at the intersection of wireless communications. So as I keep announcing, the Slack channel is open for all kinds of Q&A. So feel free to join and interact over there with the speakers.
Hi, this is John Park.
So now we have a 15-minute break, and then we'll resume back in 15 minutes at 11:35 p.m. EST. All right, everyone, we are back. So quick announcements. The conversations are happening on Split Learning channel on the Slack link. And the live streaming of the whole event is happening through YouTube. The links for the YouTube live stream are available on the workshop website. All right, let's continue with our agenda. So moving on to the next research talk. We have Gary B and some work that I did with him during my internship at Triple Blind. And this work is on blind learning, an efficient privacy-preserving approach for distributed learning.
Triple Blind is a startup that offers digital privacy as a service. In this video, I will be talking about one of our services called Blind Learning, which is an efficient privacy-preserving approach for distributed learning. It is worth mentioning here that blind learning is actually a set of protocols and algorithms that enable advanced data analysis and training of machine learning models on distributed datasets. However, in this video, I'll use the term blind learning to explicitly refer to our distributed learning protocol for neural networks, which is built on top of split learning. Before I explain the protocol, however, let us take a quick look at the motivation for this work by identifying the privacy pain points in a typical machine learning lifecycle. Given a well-defined problem that requires a machine learning solution, the data scientists often starts by collecting, processing, and analyzing proper data to be consumed by some machine learning algorithm. It is well known that in order to build a robust machine learning model, specifically deep learning models, it is very important to use large amounts of data to build a powerful, robust, and fair models. However, data sharing among data owners is extremely difficult because of privacy regulations, data localization, and competition. Once we have proper data, we start training the machine learning model. And because machine learning models are programs or functions that generalize from data, they could actually leak data during the distributed training process. In addition, the privacy of the model itself could also be compromised. And finally, when we have a good model, the model is deployed and ready for inference. And at this stage, it is susceptible to several privacy concerns, including indirect data leakage, the user data that is used in the inference process, and the model privacy or its intellectual property. To address most of these challenges, specifically data sharing, several distributed learning paradigms have been proposed. One of the most popular approaches is federated learning. And in the most straightforward setup, the protocol is orchestrated by a central server that manages the client's trainings and maintains a master copy called the global model. Generally speaking, the global model is generated at the server and it makes it available to all remote clients. Each one of the remote clients train the local copy of the model for a certain number of epochs and then share the updates with the server. The server aggregates those updates in some form, such as averaging these models, and then creates the global model, and this concludes one global training ground. The main advantage of federated learning is that it sends the model to the data, and therefore the data never leaves the data owner premises. Some of the main challenges of federated learning include direct data leakage, the model privacy is compromised, and the protocol requires large network bandwidth. In addition, it requires expensive computational resources at the client side. To address most of the challenges of federated learning, a new innovative technique called split learning was invented at MIT. Basically, split learning enables distributed learning by partitioning the neural network into consecutive chunks of layers among various parties. In its simplest form, each one of the clients has an identical part of the network, while the server has the other part of the network. Each one of the clients does a forward propagation up to the cut or the split layer, and then sends the output of this layer, which is also referred to as smashed data, to the server, which then continues the forward propagation using the smashed data as an input. The server then calculates the loss function, does a backward propagation, and sends the gradients of the smashed data back to the client. And in the first standard approach of split learning, this process is done in a sequential round-robin fashion, one client at a time. And the main advantages of split learning is that the training data never leaves the premises of the data owner. Another very important advantage is that split learning enhances the privacy of the model itself, since unlike federated learning that shares the entire model with all clients, in split learning, we only share one part of the model with the rest of the clients. Split learning also reduces the computational burdens on the clients because the clients train only part of the neural network. Another advantage is that split learning reduces the network bandwidth because it only exchanges a single layer of outputs with a server. And finally, and most importantly, it is also safe to assume that the models produced using split learning will always converge to the same level of models trained using the standard centralized procedure. However, some of the main challenges of split learning still include direct data leakage, and that split learning is slow to train due to the sequential round-based training. To this end, we present our distributed learning protocol called blind learning. The protocol is built on top of split learning and extends its functionality to overcome the challenges of split learning, specifically the data leakage and sequential training. In blind learning, each client receives an identical share of the model and all train in parallel. Smashed data is then sent to the server to complete the forward propagation process. The loss value is calculated for each client and then aggregated at the server's network using some different mechanisms based on the underlying approach and the nature of the datasets. Then the server tests the backward propagation and sends the gradients to each one of the clients to update their local shares of the model. The main goals of our blind learning is to enhance the privacy of the data. And in this case, the data never leaves the premises of the client, enhances the privacy of the model because, again, we are only sharing parts of the model with the clients. And on top of that, we are reducing the direct data leakage that is caused by exchanging the smashed data with the server. So the main characteristics of blind learning is that it trains clients in parallel. It uses some averaging techniques to aggregate the server's results, and it also uses advanced techniques to aggregate the client's results. And then it uses distance correlation measurements to reduce the direct data leakage during training. Let's take a look at one of our aggregation methods at the server side. And this algorithm depends on using an averaged loss value from all clients to carry out a single back propagation process at the server side, and then shares the gradients with all the clients. This approach is suitable and efficient for the case of IID datasets. And what we see here is the general formula for the loss function when including the distance correlation measurement, whose main goal is to reduce the direct data leakage during training. What we see on the right is the actual utility loss function, such as the cross entropy loss. And what we see here on the left is a specialized data correlation metric that aims to reduce the correlation between the input data and the activations of the split layer. In other words, we want to optimize the values of the split layer outputs or the smash data in such a way that this smash data can be used to carry out a meaningful forward propagation at the server side. But those same activations or smash data should not be useful to reconstruct the raw data. All right, I'm very excited now to show a quick demo of blind learning protocol in action using the Triple Blinds platform. I'll use the Fashion MNIST dataset for the demo purposes. However, we assume that I do not have access to such a dataset and it is not freely available online. So first, I'll have to find this dataset and then use Triple Blind to enable distributed privacy-preserving training using that dataset. The first thing I'm going to do is to visit the main Triple Blind application webpage, where I can actually use the Datasets Explorer to find datasets of interest. And in this example, I'm going to look for the Fashion MNIST dataset. I see there's one available here, and the data owner of this dataset have left some very useful information, such as the number of records, the labels, and the size of these images. There's also the price, the agreements, and a rich view of the characteristics of dataset. However, to be able to point towards this dataset that I would like to use it in my code, I can simply copy the ID of the dataset and come to my actual working environment. So here I am using Jupyter Notebook. I have already installed the TripleBlind's SDK that will allow me to run the blind learning protocol. To start the blind learning protocol is very easy. I'm going to import the required or the necessary libraries, specifically the TripleBlind one. I'm going to create a pointer towards the data set of interest by pasting its ID over here. I'm going to run the cell, and I see that we have successfully pointed towards that data set, but still we do not have access to it. Before accessing the data set, I'm going to create a data processor that's going to do some manipulation or transformations on the data, such as resizing it, defining the color of the images, and whether the channels are first or last, and the data type. I'm going to run the cell. And here's the fun part where we are going to build our neural network using the TripleBlind SDK API for the network builder. And everything is very similar to what you're familiar to in Keras or TensorFlow when building sequential models. The only thing different here is that we have a specific type of layers called the split layer. And the split layer defines where to split the actual model. And let's run this. And this is another fun part where we actually define all the parameters for the training job. So the loss function, the optimizer, the number of epochs, the test size of the data set, so on and so forth. I'm also going to run this. And here's the actual training. I'm going to create a training job and define the parameters and the data set I would like to use, and run this cell. You will notice that the training is right now waiting on something. And of course, it is waiting on the approval of the dataset owner for me to be able to use their dataset. So now I'm going to play the role of the dataset owner, and I'm going to enter the TripleBlind application. I see that there's an access request to use my Fashion MNIST dataset. I can approve it, or I can actually contact the data scientist that wishes to use this dataset to make a better agreement. But for this example, I'm just going to approve this job. If I go back to my notebook, I see that the training has already started, and we defined 2 epochs. So right now we are in epoch 1 of 2. And we see that the first epoch is done, and the accuracy is about 82% on 3,000 images. Once the training is done, I'm the model owner. I can download the model, or I could expose it as well at TripleBlind for others to use. We also provide secure protocols for inferences, including secure multi-party computations. So this concludes our video for the blind learning protocol for neural networks. And here I would like to acknowledge our team members. I'd like also to acknowledge the interns of TripleBlind, specifically Praneeth Vipakuma from MIT, who made significant contributions to the distance correlation for reducing the direct data leakage from the split layer. We also thank Caitlin Storm from Johns Hopkins University and Cheryl McCart from Purdue University. Thank you very much for watching. If you have any questions, please reach out and visit our website at TripleBlind.ai.
Thank you, Garib. That was a wonderful talk. So, yep, Q&A is happening in Slack. We see the Slack channel is growing quick into a large group. Another quick announcement I'd like to kind of make or kind of remind is, like Ramesh put it in the beginning in his opening remarks, I think this is a great opportunity to form a community that can write a reasonable survey paper on the advances in open problems in split learning. So as the 2-day event, the 2 days program is kind of reasonably packed, we would reach out to the speakers and researchers with potential interest in this project offline after a few weeks after the event. So yep, for Q&A, reach out on the Slack channel. So let's move on to the next speaker.
Hello, everyone. My name is Garib.
Okay, yeah, let's move to the next speaker. There we go.
Hello, everyone.
So we have training neural networks using features replay by Zuyan Hu, Bin-Gu, and Heng Huang from Google, MBZ UAI, JD Finance America Corporation, and University of Pittsburgh.
I'm Zhou Ho from Google. Today, I'm presenting the paper, Training Neural Networks Using Features Replay. This is joint work with Professor Bing Gu and Professor Han Huang. The success of deep learning depends on three important factors: big model, big data, and big computing. In terms of big model, let's take the ImageNet classification as the example. In the figure, we can see that from GoogleNet, which had about 4 or 5 million parameters, to the EnvoyNet, which had about 600 million parameters. The top-down accuracy on ImageNet dataset can be improved from 75% to 85%. We can see that the bigger model we have, the better performance we can achieve. To optimize the neural networks, we need to use the stochastic gradient descent. Let's take the 3-layer neural network as an example. Each layer, we have the parameters W1, W2, and W3, and the loss function L. As long as we compute gradients regarding to regarding to the weights in different layers, we can use the SGD to update the model. To compute gradients for deep neural networks, we use the backpropagation algorithm. The BP algorithm. The BP algorithm has 2 passes: the forward pass and the backward pass. In the forward pass, the input H0T is forwarded from layer 1 to layer 3, and we have loss function after the forward pass. In the backward pass, different layers will compute gradients regarding to its input and model weights. So in layer 3, it will compute the gradients regarding H2T and W3T. After the computation in layer 3 is done, it will pass partial LT or partial H2T to layer 2. Then layer 2 compute the gradients of partial LT over partial H1T and the partial LT over partial W2. In the computation, it will require the gradient result from layer 3, which is a partial LT over partial W over partial H2T. After the computation in layer 2 is done, layer 1 will receive the result from layer 2 and compute gradients regarding to W1. So this is the process of BP algorithm. However, there is a problem in the BP algorithm, which is called backward locking. The backward locking means that when layer 3 is doing the computation, layer 1, layer 2 will be idle because the computation in layer 1 and layer 2 are dependent on the outputs of layer 3. Because of this problem, if we split layer 1 and layer 2, layer 3 to different devices, we cannot parallelize the computation in different layers because of the backward locking problem. To solve this problem, we propose the decoupled delay gradient. The idea is very simple. We just need to make different layers compute gradients using different samples. For layer 1, it use the samples from time step A, and layer 2, it uses the samples from time step B, and layer 3 using samples from time step C. And as long as A not equal to B and not equal to C, different layers are independent from each other. The difficulty is that when layer 1 want to compute gradients regarding to the partial LA or partial W1, it need the partial LA or partial H1A should exist in layer 1. Layer 2 also have the same problem. To solve this problem, we just need to make A smaller than B and smaller than C. For example, if we make A equal to times T minus 2, B equal to T minus 1, and C equal to T. Let's take the figures as example. In the forward pass, the input H0T is forwarded from layer 1 to layer 3, which is similar to the BP algorithm. The difference happens at the backward pass. In the backward pass, layer 3 will compute gradients using samples from time step D, and the result, partial LT over partial H2T, are computed. Then it will pass this value to layer 2. Layer 2
In layer 2, instead of computing the sample gradients using samples from time step t, layer 2 will compute the gradients using samples from time step t-1. In this way, because partial L t-1 or partial H2 t-1 has already been received from layer 3 in the previous time step. So at time step t, layer 2 and layer 3 are independent from each other. Similarly, in layer 1, it just need to use the results partial L t-2 or partial H1 t-2 from layer 2 in previous time step, and the computing gradients using the samples from time step t-2. In this way, layer 1, layer 2, and layer 3 are computing gradients using samples from different time steps, and they are independent from each other at time step t. So suppose we have a 12-layer neural network, and each 3 layer are placed on different devices. So there are 4 devices or 4 GPUs. By using the decoupled delay algorithm, module 1, module 2, and module 3 can compute it in parallel. However, there is one issue, which is using the BP decoupled delay DDG algorithm or decoupled delay gradient algorithm, layer 1, layer 2, layer 3 should store the activations of the previous time steps, which is very space consuming. To solve this problem, we propose to use the feature replay algorithm. So for example, in module 1, instead of storing the activations in different time steps, module 1 will, in time step t, to compute the gradients using samples from time step t-3, you just need to input the input of the module 1 h0 t-3 to the module, and using the model weight wt to recompute the activations at layer 1, layer 2, and layer 3, which are to the h1t, to the h2t, and to the h3t separately. In this way, we can reduce the space complexity to big O L plus k square, where the L means the number of layers and the k means the number of devices. Because the number of layers are really much bigger than number of devices k, so the space complexity is very similar to the memory consumption of the BP algorithm. In the paper, we also analyze the convergence rate of the proposed algorithm. We propose to analyze the convergence, we propose a new sufficient direction assumption. We assume that the expectation of the gradient computed using the feature replay algorithm is in a positive direction, which is regarding to the sigma, some constant sigma, and it is bigger than 0. To verify the assumption is reasonable in the deep learning, we visualize the variations of sigma in different modules on the ResNet 100.01. In the figure, there are 2 observations. The first is that all the sigmas are bigger than 0. And the second, in the sigma in the module layers is smaller than the module layers, higher layers in the beginning of the training. However, after the optimization, sigma value of different modules will be very close to each other and very close to 1. So by using the assumption, we can prove that the feature replay algorithm can converge to a critical point with the sublinear convergence rate, which is similar to the normal stochastic gradient descent algorithm. In the paper, we also execute extensive algorithm experiments to verify the performance of the feature replay algorithm. In the first figure, we can see that feature replay algorithm converges very similar to the BP algorithm, and if we increase number of GPUs, we can reduce the training time significantly. If the number of GPUs is 4, the completion time of feature replay algorithm is just about half of the training time of the BP algorithm. In the figure 2, we also compare the memory consumption for different algorithms, BP, DDG, and the feature FR. We can see that feature algorithm consumes very close memory as BP algorithm. In the table, we conducted experiments on different datasets and different modules. In the table, we can see that feature algorithm can achieve a better solution than the BP and DDG algorithm. We suppose that we suppose that the reason for the feature algorithm better than the BP algorithm is that in the training, the noise can serve as some regularization in the training, so it could improve the generalization performance. In summary, to parallelize the training of the big model on multiple machines, first, we break the backward lock in the BP algorithm. Secondly, we reduce the memory using feature algorithm. The codes are available in this website, and thank you very much.
Thank you for the talk. It's question time back in Q&A on Slack. And as we move on, we have our lunch break coming up. So we're going to join back at 1:25, and then we're going to have another keynote speaker from Facebook AI, some more research talks, and there's an exciting Code Your Split Learning session that Abhishek Singh is going to be presenting. So it's a hands-on workshop and more of a coding workshop, and we conclude the day with that. See everyone, continue the conversations. We'll see you after lunch break.
Hello, are you able to hear me?
Hey, yes, we can hear you.
Okay, thank you.
Hello, everyone. You're back from the lunch. We have another very exciting keynote speaker, Geeta Chauhan. She heads the PyTorch Partner Engineering at Facebook AI. And I give it over to Geeta Chauhan, and then there's going to be a 5 to 7 minute Q&A in the end. We're going to relay some questions back and forth. It's all yours. Looking forward. Can you just unmute?
Are you able to hear me?
Yes, we are good now. Okay, good to go. Thank you.
Okay. Yeah, welcome everyone. Excited to have you join for my talk on building AI with security and privacy in mind. So we'll start off by looking at privacy challenges in AI. Then we will dive into the privacy preserving ML techniques, specifically for distributed ML. And we will look at the tools and resources. So let's dive into the privacy challenges in AI. If you look at the current AI systems, they are like the closed source software of the 90s. One has to bring all the data into large central data lakes and do the processing on that, which poses many challenges around privacy. One has to consider the privacy trade-offs and balance the needs of protecting the consumer and training the AI model to give the best results. There is tension around data minimization versus retention for long-term, which is the current norm in the industry. Consumers have a very poor understanding of how their data gets used by AI systems, and this gets compounded further with large proliferation of AI models. As the new AI systems evolve, it magnifies the ability to use the information in ways that can intrude on privacy interests of the consumers. The increasingly sensitive nature of data used in the AI models and for research raises other privacy challenges. For example, re-identification and de-anonymization of users' data when it is combined with external sources of publicly available data. How and from where can we source data that is free of bias and move into an era of ethical sourcing of data similar to what exists in fair trade for coffee? The data needs of AI models have to be balanced against those of the consumers and regulations. On the data for AI model side, collected data needs a business justification, so one has to ensure that AI inputs are important to the model for best performance. On the consumer side, a more proactive, user-centric approach is needed for building solutions by analyzing what consumers are comfortable in sharing versus the benefits they get from the solution. On the government regulatory side, one has to consider the laws and regulations like GDPR, CCPA, specific to the region and use case to guide the development. And for the business side, conscious effort has to be made to not collect data or use certain types of data out of concern, either for the business or responsible AI elements. So next, we will dive into the major privacy preserving ML techniques and then zoom in to the distributed ML side. So there are a range of privacy preserving ML techniques, homomorphic encryption, differential privacy, secure multi-party computation, on-device local computation, trusted execution, and solution, the federated learning solution. Each of these techniques covers different aspects of privacy, either for the inputs, the outputs, or the models. And by combining all of these together, one can build an end-to-end secure privacy preserving solution. So let's look at some of these techniques. Homomorphic encryption is a privacy preserving approach where the inputs, outputs, and the intermediate data values are always encrypted. Here, the operations are computed directly on the encrypted data instead of having to decrypt it first. This allows the developers to implement training or inference without ever seeing user data, and one can use a shared pool of computing resources in the cloud while preserving privacy. So in this example here, you see the numbers 3 and 5 are homomorphically encrypted to generate the cipher A and cipher B, and then all the computations happens on these encrypted numbers, and it is as if the computation was happening directly. So if you multiply 2 with cipher A, you get a value of C, and if you add cipher A and B, you get the value 8. Differential privacy is based on the seminal work by Cynthia Dwork and provides a strict mathematical definition of privacy in the context of statistical and machine learning. In simple terms, it is a promise that a curator of data makes to a subject providing the data that they will not be adversely affected by sharing their data no matter what other data or studies are available. For example, their data will not be able to disclose their identity when combined with other sources of data. As a result, it enables the collection, analysis, and sharing of statistical estimates such as averages, contingency tables, and synthetic data based on personal data while protecting the privacy of the individuals in the data. Mathematically, for two databases that differ in a single person's contribution, the D and the D prime, the output of the mechanism on D is nearly the same as its output on D prime. So more precisely, the definition requires that for all possible outputs, the two distributions must be multiplicatively close to one another. Here, we are looking at the epsilon delta differential privacy guarantee, which has two parameters, epsilon and delta. Think of epsilon as a small constant that bounds information leakage, and delta as the probability that guarantees fails. The differential privacy noise is added to user data before it is shared with other parties. The noise is applied, a strict upper bound can be set on the amount of information leakage within any particular query. With this, one can put guards against linkage attacks where publicly available data overlaps too closely with data held in anonymized data sets. For example, of a linkage attack is when the former governor of Massachusetts had his sensitive medical records re-identified using overlap with his voter registration data. Secure multi-party computation is a subfield of cryptography with the goal of creating methods for parties to jointly compute a function over their inputs while keeping those inputs private. It distributes the computation across multiple parties where no individual party can see the other party's data. Multiple parties possess parts of the data, and none of the parties can reconstruct the actual data without collaboration of all the parties. Yet the parties can evaluate the function together. So if you compare differential privacy and secure MPC, the differential privacy describes the what part of privacy, and secure MPC describes the how to do it in a secure manner. So this is an example of an actual computation. So the number 12 is split across the two parties, the party A and B, and then each party is doing the computation at their end, and you are able to combine the numbers and get the actual results. On-device computation can be used in training the models, allowing local personalization of model and then running inferences without data leaving the device. So this can be used in examples like when you're running image recognition models on an image stream from a phone's camera, or when translating text in a private messaging app. Clustered execution environments or secure enclave is a secure area of a main processor or a chip. Foreign data that are loaded inside the secure enclave are protected with respect to confidentiality and integrity. It provides security features such as isolated execution. Here, the user data used for ML model training and prediction stays in an environment secured at the user hardware level. As an example, this can be used for creating a privacy-preserving environment for electronic voting when used on the user's devices. Further, with the trusted execution environment, a cloud provider can provide clients with a guarantee about exactly what they are doing with the client's data, and it guarantees that they did not do anything else. Now, federated learning is a distributed machine learning approach that enables training on large data sets, such as mobile phones, while ensuring the data stays local. So if we take a look at the walk through the whole process. So the devices check in with the server. Subset of these devices are selected to participate in the federated learning. Each of the selected device then downloads the model from the server. The trained model is trained on the device with the local data, and then the model updates, the gradients are sent back to the server. The central server securely aggregates gradients from all participating devices to update the model. And this is repeated until the model converges. And on parallel on the server side, there's a monitoring and snapshotting goes on to monitor the process. Once a final new model is available, it is sent back to the devices and it provides an improved performance by using the updates across the various distributed devices in the network without revealing any of the private information used to train the model. Now, each of the techniques in this privacy-preserving ML offers different aspects of privacy. So in order to build a fully secure system, you have to combine all these techniques together to get a better solution. So for example, with homomorphic encryption, the data is encrypted, it encrypts the computations, you get zero knowledge proof for the intermediate results. Some information may leak, however, even the output is revealed. With differential privacy, there is low probability guarantee on the output, and it prevents linkage attacks. With secure MPC, it also offers zero knowledge proof for intermediate results. There is no information leakage through the transcript of the computation. However, information can leak when the other party's output is revealed. With on-device computation, there is local data privacy, but you are limited by the amount of compute and memory that is available on the device, and there is reduced ability to aggregate across multiple devices. With trusted execution environments, you get the hardware isolated environment, but again, it is limited in memory. You can do secure, you can secure the data and the model, and you can also do remote attestation. With federated learning, it is decentralized, so training takes a longer time. It happens over heterogeneous devices, so it has its own challenges. For example, the network transmission cost of the models and the downloads of the gradient updates that can be quite expensive. So one has to take all this into consideration. So if we take a look at our federated learning example and try to see from a privacy perspective, what is the state, what can be seen across the network, there are several different viewpoints from the device, the server, the network, and the consumer perspective. On the device side, one sees the intermediate model state. On the server side, there is the ephemeral model updates. Network sees the encrypted model updates, and the developer sees the intermediate model state, and the world sees the final model state. So the device side model is still prone to remembering the user data. On server side, if it is compromised, it can again individual details can be deduced during the update of the gradient. So for dealing with various adversarial attack vectors, can we do anything better? And this is where we combine all these solutions together. So with federated learning, secure enclaves, differential privacy, secure aggregation, you get a much better solution. So with additional privacy. So here, the client gets a secure enclave private key, and they clip the model updates before adding the random mask. On the server side, the logic for computing the sum of the masks and the differential privacy noise is moved inside secure enclave with attestation. The server and the developer only sees the aggregated data, and the final model contains the differential privacy noise. This results in greater security. On the device side, the updates are randomly masked, and ephemeral model updates are sent to the server. Secure aggregation of the updates of the models happens on the server side, and the model is available with a user-level differential privacy. So when you're dealing with very large models now, it is very difficult to train these models on the small devices, and you have to employ the split learning techniques. So we take a look at horizontal split learning. Here, the model is cut into two parts. Part of the model resides on the server, and part of the model resides on the device. So on the server side, it owns all the features, and the device owns all the labels. So the server performs the forward and the backward passes for most of the model architecture. and the device takes care of the very few thin layers just after the cut layer which reside on the device. So here the devices will send the model gradients of the cut layer, and after the cut layer, you will use it along with techniques like secure enclaves to send the data securely. Now, horizontal split learning also has its own privacy challenges. So the label privacy challenge is a big one. Here one can, by observing the model gradients before cut layer, the server can infer private training labels. So different threat models have to be assessed in this context. You can put the output layer on the device. In this case, one can leverage the last hidden layer gradients to infer the label. If you put the output layer and the last hidden layer on the device, in this case, one can leverage the second last layer gradient to infer the label. So what we have found is that with more layers on the device, it helps to preserve the label privacy against the privacy-based attacks. So the possible solutions are that you can protect the label, you can put the cut layer by enclosing it in secure enclaves like SGX. You can use techniques like gradient shuffling, obfuscation, or the differential private SGD. In vertical split learning, there is an ensemble of vertical models with separate models for each vertical or cohort. So here one has to employ different techniques for how to do this vertical cohort selection. For example, if you use, you can use the same global features across all the verticals, or you can have optimized features based on verticals. So this is still an active area of research, how to come up with the right optimal strategies, and depends highly on the use case that you're applying it for. Okay. So far we mainly talked about the training side. So on the inference side for the predictions, we recently released our paper on ResiliNet, which addresses the failure-based resilient inference. So it takes care of situations where distributed inference is happening. So this could be when you're collecting the inference across a group of IoT devices, for example, in a factory or a hospital setting, and you have the data is too large to send to the server. So all these IoT devices are collaborating to generate the actual inference and sending that. So here the skip hyperconnection technique is used, and the resilient network, the hyperconnections only get activated on failure. So that's why you're able to see the speed up compared to some of the other techniques. So let's look at if you're trying to design a system for privacy, you have to consider privacy by design right from the beginning to be really successful. So here are some of the best practices and considerations. So first of all, provide user control for opt-in versus opt-out, and make opt-in the default approach. Only collect the data that is needed for the application or solution. Limit the time period of retention of the data versus hanging on to it forever. Provide transparency and educate users on how the AI system will use and process their data. Set up privacy review boards and prioritize consumer privacy across the organization. Use responsible AI principles and commit to it across the entire development cycle. Privacy by design is a continuous iterative process and not something which comes as an afterthought at the end. At every stage of the machine learning pipeline, one needs to assess and evaluate the privacy and fairness goals and verify they are being met. And it requires a very different kind of expertise, and you have to take inputs from a range of stakeholders. So if you zoom in, this is what the process looks like. So first, we want to understand what are the product goals, the policy and implementation within the broader social context where the system will be used. Next, we hold conversations with stakeholders to reach consensus to outline measurement and mitigation plans. So this will have things like, how is the system performing? Why does it perform that way? What are the other questions that we need to be asking ourselves? Then the measurement is followed by mitigation of privacy and fairness concerns and an ongoing process for monitoring so that we can make things better. So on the Facebook AI side, we have released a few tools and libraries for the privacy-preserving ML space. Krypton, which is a PyTorch platform for research in machine learning using secure computation techniques, starting with the secure multi-party computation. Opacus, which is the PyTorch differential privacy library that we launched earlier last year, and we collaborate with OpenMinds, who gave a talk earlier in the session today. So Krypton is a platform for research at the intersection of machine learning and secure MPC. It targets machine learning researchers who are not cryptography experts, interested in experimenting with ML models using secure MPC techniques and getting a realistic view of what is possible, what is difficult, how efficient their techniques are, etc. So they can run all these experiments on the platform. It is based on secret sharing, DGW and Beaver triples, which is compatible with the SPDZ paradigm. It extends PyTorch with which is a leading ML framework, and it implements what is table stakes for ML systems like reverse mode autograd, GPU support. So overall, Krypton's ambition is to make switching from PyTorch to the Krypton backend as easy as replacing the import statement. So from import torch, you go to import Krypton as torch and just start using and coding as normal. Opacus is a library that enables training PyTorch models with differential privacy. It supports training with minimal code changes required on the client, has little impact on training performance, and allows the client to online track the privacy budget expanded at any given moment in time. Training the differential privacy is as simple as instantiating a privacy engine. Leveraging the autograd hooks in PyTorch, Opacus can compute batched per sample gradients, resulting in an order of magnitude speed up compared with existing differential privacy libraries that rely on micro-batching. And it uses a cryptographically safe pseudo-random number generator for its security critical. And some of the other techniques to look at are active federated learning. So this does the first user cohort selection by using active adaptation of model state and data. So in this diagram here, you see the red and the blue dots. They show the private data on the devices. With each step, the client sends updates to the server, and then the server converts these individual values into probabilities of each client selected for the next batch. And then the selection process happens for the next training batch, which is random, and it uses this probability to do the selection. So by using this active federated learning, we are able to train models with 20 to 70% fewer iterations for the same performance. We also recently published a fair resource allocation in federated learning paper. So here we introduced the Q-fair FL optimization device objective for fair resource allocation. So you can see the test accuracies across the different federated learning data sets. This was inspired by wireless networks to encourage fairer accuracy across the distribution of the devices. And it uses the Q-fed average, a scalable communication efficient solver for massive networks. Another paper that we published recently is DITO, a multitask objective that we introduced for solving the competing concerns for robustness and fairness. So it provides more robust, accurate, and fair results compared to some of the other techniques that are available. So I would highly encourage you guys to take a look at Papers with Code, which is a great resource for finding the latest research papers and the corresponding code for it. And last year we did the integration with Archive, which is the key step forward for reproducible research. So now if you go to Archive and look for a paper, you just click on the code tab and you can directly jump to the code corresponding to the paper. Recently, we also added support for datasets in Papers with Code. And if you take a look at the federated learning task on Papers with Code, you will see that already, like, we have 7 data sets published for federated learning and a whole host of papers with both with code and without code. Okay, so what are some of the use cases where you can use this? So, there are startups like Aukin who are making use of federated learning for cancer research to train their models with data sets from different hospitals to build a combined better model for all parties. Similar things can be done for COVID-19 solutions by combining insights from data across hospitals and government agencies. Microsoft is using in the PhotoDNA project, it provides a cloud service to remove photos of child exploitation. You can use federated learning to bridge across enterprise silos to build models by combining data from different departments. So I'd like you to invite you to think about what problems you will solve using privacy-preserving ML techniques. And please reach out to us if you have questions or you would like to run some new experiments. If you're looking to learn more, we have created a great series of courses with Andrew Trask and OpenMind. There's a Building Secure and Private AI course on Udacity, and a new learning series that was launched at the start of this year on courses.openmind.org. And here are some more resources for you to get started. And now I will open it up for questions.
Thank you, Geeta. That was a very insightful talk. It was also interesting to look at the different projects at Facebook in this area. So we have a few questions on our Slack channel. First question from Chandra Thapa. What are the pros and cons for the composite solutions where you're combining TP with MPC and so forth, or any insight into what is happening when we combine is a question we have.
Yes, so thanks, Chandra. This is going to be very use case specific. And in fact, you will not blindly combine all the techniques. So for your particular use case, you will need to run experiments and see which techniques make sense to combine. That would be my advice. I would suggest that you start off with running simple experiments, do get something working with basic federated learning, and then add the other layers on top of it.
Sure, makes sense. One more question. Many of the existing privacy or formal methods like SMPC, homomorphic encryption, and secure enclaves are data agnostic. So basically the techniques are agnostic of the data itself. But the question is, if you think new techniques might be designed so that they're a little more specific to the data at hand before we privatize or make it formally private, or making the compute secure.
So I think this is still an area of active research. Unfortunately, we are still running experiments like all other companies in this space and trying to figure out what is the optimal solution that will work for a wide variety of use cases. So today, if you take a look at the current AI systems, data is visible when you are training the models, so you have insights on those. So now it requires a whole mindset shift where the data visibility will not be there, and we have to come up with these new tools of how to do training in a federated learning distributed environment where we can still get the results. I would love to give you a better answer, but this is the state of the art at present. Things are still being discovered.
Sure. Yeah. It was more of an open-ended question as well. I can see that. So one other question I was having was about the Krypton and the Opacus, if that's how you pronounce it. So I've heard of Krypton before. I'm just curious what Opacus is bringing into the table when you put in those three in that slide, along with the OpenMind PyTorch.
Yeah. So on the Opacus side, it is basically giving you, it is a library that enables the differential privacy with PyTorch. So you can do, quickly check with the privacy budget how to do the training, and it hooks into the AutoGrad hooks of the PyTorch, and you can do the dispatched per sample gradients. It computes that, and it speeds up the whole. So it's basically a differential privacy library for PyTorch.
Oh, got it. Yeah, thank you very much. This is great. Yeah, I think these are the questions. Oh, we have one more question. Looks like it's very active on Slack. Yeah, so the previous question was Abhishek Singh, by the way, and this one is Garib Garibi asking if Crypten works on Windows as well, like Windows platform.
So at present, most of these solutions, they start on Linux first. So my recommendation is to start there, build something, and in time we will add support for Windows as well. Yeah, and open up issues on GitHub. If more people upvote, then we can add prioritize and add support.
Yep, very cool. Yeah, he's thanking you for the answers. So yeah, this is fantastic. Thank you very much. We're also excited to see some of the split learning slides that you shared about the work at Facebook. Thank you for joining us, Geeta.
Thank you very much for having me.
Yep. Okay, so let me share screen. All right, everyone. So yeah, we just had a wonderful keynote talk by Geeta Chauhan. So we're moving on into our research talks section again. And as a reminder, we'd like you to be, we'll be reaching out to you regarding the advances in open problems in SL, maybe in a few weeks, so that we can set up some breakout discussions and frame the outline for this draft. And then we'll share some common, workspace tools like Overleaf and so forth, so that we can put together a survey together. Second announcement, the same announcement you've been hearing from the morning. There's a live YouTube stream going on. There's a Slack channel for any discussions, collaborations, and Q&A. So feel free to join the Slack channel. And finally, there's towards the end of the research talk session in the afternoon today, there is going to be a hands-on session where we show code. And then the goal is to code your own split learning by following our session. And we're going to be sharing code for that. There are 3 modules to these, so there'll be some modules today and then some modules tomorrow again at the end of afternoon session. All right, so that's it. Let's keep going. So the next talk is on Shredder. We've had a few people mention Shredder already in previous talks. And it's by Fatima Sadat, Miresh Kala, Mohammad Kazim Taram, Prakash, Ali Jalali, Dean, Hadi from UC San Diego, ARM, and Amazon. Well, and then a lot of other affiliated entities as well.
Hi, I'm Fatima, and I'm going to present Shredder, which is a method for training noise distributions to protect privacy of systems deploying machine learning models. So in this work, what we're targeting is prediction or inference privacy. And what this means is the privacy of queries and the raw data that we send to online cloud services to run a task for us and return the results to us. So you take a picture with your phone, you send it to a service provider, to an application to run some filters on it, and then you get the image back. So there you're sending your raw image that could have some sensitive information in it that are irrelevant to the task that the service provider is supposed to run. Or also when you call your smart home device and you ask it to run something, it's collecting information from all your surroundings. So you're sending your raw data to systems, to providers that might be compromised and you don't necessarily trust them. Now, if you want to protect the privacy of these queries, one way is to add some random accuracy agnostic noise. And in this scenario, the problem is that in order to get any meaningful privacy, you need to add a whole lot of noise, which is going to cause a lot of loss in utility. Another way is to use encryption-based methods that can offer you security, and they also have very little loss in utility. But the problem with them is that they are very computationally intensive, so they're going to cost a lot in terms of runtime. Now, an ideal model would be a model that could add noise in such a way that it takes into account the execution of the model and that it can be resilient. So you can add noise that the model is resilient to, and you're not causing loss to utility. At the same time, because it's just a noise addition, you're not really imposing any extra computational or communication costs. So you can have both acceptable utility, and also you don't need to spend a lot of time as opposed to encryption-based mechanisms, which cannot really be deployed in real-time applications yet. Now, the key idea behind Shredder is the learning of noise patterns that a model is resilient to. So normally when you're training a model, what you do is you send in a batch of data, you calculate the gradients, and then you update the weights using backprop. Now, what we're thinking is that you can add noise to any intermediate activation to any layer in this setup. And then here, you can also like freeze the network. So if the model is already deployed, you don't really need to change the model. You freeze it. And instead of updating the weights, you will be updating this noise tensor. So you're learning noise patterns that the model is resilient to. And what is good about this setup is that it can work for any objective function. So you don't really need to be tied to a specific function. And also it's non-intrusive to the model. So if you have a model, it's already trained and deployed, you don't really need to change the weights of that model. You don't need to update it. And also you can add this additive noise to any layer and it can work. Now, the execution model that we're assuming is a kind of a split learning setup. So we cut the neural network into two sections. The first section is deployed on the edge device and the second one on the cloud. And to the first one, once we've run the first partition, we add some noise that is sampled from these noise patterns, these noise distributions that we know the model is resilient to. And then we send these noisy intermediate activations to the cloud to run the rest of the inference task. Now, how do we learn these noise distributions that the model is supposed to be resilient to? In order to do that, what we do is first we take a pre-trained model that we want to do this to, we take it and we partition it into two segments. Now, the partitioning is also important because you want to take into account the communication and computation costs, the trade-off here, and also you want to take into account the restrictions that your edge device has. So considering all of these, we find the optimal cutting point and we split the network in that cutting point. We then initialize a noise tensor with a random sample from a Laplace distribution. And then we execute the first DNN segment and we add this noise and we get noisy activations. We then feed these noisy activations to we send them to the cloud, we feed them to the rest of the network, and we get the output of the network. So we get the logits, and then we run one round of backprop to update the parameters. Now, at every set of iterations, what we do is we check the accuracy on a kind of held out validation set to see if we have reached a desired accuracy level that we wanted to. If we haven't, we go back, we like sample another batch of data, we continue the training. But if we have, then what we do is we fit a distribution to this noise tensor that we had. We feed a Laplace distribution. We collect the parameters of this Laplace distribution, and we save them along with the order of the noise elements. So we create a tuple, we save them, and we collect this tuple. Now, what is this loss function that we're using to train? The loss function is relatively simple. It has two main terms. The first one is a cross entropy loss, which is there to minimize the classification error. So you want to make sure that whatever main task your model was supposed to run, it's still running it with an acceptable level of accuracy. But at the same time, you want to increase the noise because you want to lose information. So you want to get privacy by losing any information that is not going to be related to this task. So we also have this term that is trying to maximize the standard deviation of the noise. And we also have a knob, alpha, which is there to help you control the accuracy privacy trade-off. Now, once we have collected these noise distribution parameters and their orders, what we do during inference that we've deployed this model, we want to add noise to queries. What we do is we randomly choose a distribution, like a tuple from our collection, a tuple of distribution and orders. we sample from that distribution. So we have a Laplace distribution, we have the parameters, we take a sample and we populate this noise tensor. We then reorder the elements to match the saved order that we had, and we add this noise to our intermediate activations, and we send it off to the cloud. And the cloud runs the rest of the computation and gives us back the final results. For experiments, we used a Jetson TX2 board as an edge device, and we also used a server with a Titan XP GPU as our cloud, and we use PyTorch on both these devices to run the neural networks. Now, our main result is our accuracy privacy trade-off. So on the accuracy axis, you can see the loss in accuracy, and for privacy, we are measuring information loss in bits. So how much information is lost between this, how much mutual information is lost between the original raw image and the activation that you're sending. And the zero leakage is like total loss of information. So if you get to this red line, it basically says that you have lost all the information that was originally there. And we can see that with the more accuracy we lose, the more we are willing to sacrifice utility, we can get closer to this line. And the best kind of trade-off, it's the knee of this curve that gives you like acceptable levels in information loss, and you also get an acceptable accuracy loss. Another thing that is really important about this work, and in general about split learning, is that you can sometimes even get improvements in the overall runtime because of the communication trade-offs. So once you're sending the entire query, you're spending a lot of time for communication. Whereas if you send an intermediate activation, which is a smaller, you're spending less time in communication and you're adding a little computation time. So in general, on many of the benchmarks, we saw that we can even get a speed up over a cloud-only baseline that you can see here for the networks. So to summarize, Shredder can give you faster execution and enhanced privacy, but it's also too heuristic based. So maybe like the distributions that you get, maybe not all of them work. So you have to test them and you have to find this distribution that really works for you. Thank you for listening to my talk.
Thank you, Fatima. So we have a few, I guess, questions are being typed currently. So I see you are already on the Slack channel. So as the questions come along, you can reply to them on the Slack channel. I guess I can read out one question that has just come in, and then the rest you can handle over Slack. So one question is, how do you define leakage in your setting?
Hi, thank you. So we define leakage by the amount of mutual information between the raw images and the intermediate noisy activations that we're sending. And so this is, we calculate this for like a conventional setup where you have a normally trained neural network, and then we calculate the same mutual information for our noisy version of intermediate activations. And then we compare these two. So that is the leakage, like how much change do you have if you send the normal intermediate activations versus the noisy ones? Like what is the difference between the mutual information they have with the raw image? I hope that answers. I can elaborate on Slack.
On Slack, yeah. So, okay, maybe you can give two more quicker questions. I think there's a lot of activity on this. So, okay, one is from me. So wouldn't you also recommend refreshing your collection of distributions? Because you're anyway sampling random parameters for the distribution, but then after a while.
Yeah, exactly. Yeah, that is a really good point. So one thing that we were thinking of, like if this is to be deployed in a larger scale, it would be good to have these collections refreshed like every hour or so for like different devices, so that we can like have an extra level of randomness and protection on top of it. Yeah.
Right, yeah. Especially the collections should be very far off in total variation or some tail distance.
Exactly, yeah, that's a very good point, thank you.
Interesting, yeah, okay. And then the final one is from Abhishek saying, any thoughts on applying Shredder for training? So something like DPSGD, but we noise the activations using Shredder instead of DPSGD where the parameters are noised.
I think that is a really good avenue. However, I'm not sure how the guarantees can be recalculated then.
Sure, of course.
Like how much information is the model really memorizing? Yeah, I think that needs to, be further scrutinized so that we can measure it. Yeah.
Right. And I guess questions are coming in as we talk. So you can carry out and reply on Slack.
Sure. Great. Thank you so much.
Great. Thank you.
Thanks.
Okay, so we carry on to the next research talk.
Hi.
This is by Ali Abedi and Sheroz S. Khan from KITE, University Health Network Canada, University of Toronto, Canada. They're going to be talking about FedSL, Federated Split Learning on distributed sequential data in RNNs.
Hi, everyone. My name is Sheroz Khan. I'm a scientist at KITE Research Institute, University Health Network Canada, and also an assistant professor at the Biomedical Engineering Institute, University of Toronto. And today I have Dr. Ali Abedi, who's a postdoctoral researcher in our team, and we are very excited to discuss our paper on federated split learning on distributed sequential data. So as you know, that in conventional machine learning algorithms, models are usually developed in a centralized setting. That is, the data generated by local clients are firstly aggregated into a server or PC, and then the training is performed on the server or the PC. However, the client's personal data is privacy sensitive and can be large in quantity, for example, the healthcare data or the video data, which disqualifies centralized machine learning methods from sending local data to the server. Now, federated learning and split learning are distributed collaborative machine learning techniques that decouple model training from the need for direct access to the raw data of clients. Now, I'm going to tell you a little bit about different types of data that are available. So, first is the horizontal data. In horizontal data distribution, different clients contain unique training samples with unique sample IDs. There are not different versions of one's sample ID in different clients. Different training samples on different clients are represented by the same feature. Then we have vertical distributed data in which different clients contain different versions of the same training samples with the same sample IDs, but represented by different features. And then we have sequential distributed data in which the training samples are sequences. So for example, from time stamp 1 to time stamp n with multiple segments. Now these multiple segment sequential data are distributed across clients. Now consecutive segments of training sequences are distributed across different clients. And consecutive segments of training sequences are generated and are available on different clients. Now, to give you an example of sequential partition data, suppose one patient is consecutively admitted to 2 different hospitals, each recording sequential vital signs of the patient, for example, heart rate. In this case, the heart rate of the patient is sequentially distributed across 2 hospitals, or in our case, 2 clients. This multiple segment sequential data can be used to train machine learning models to predict, for example, mortality of a patient. The existing federated learning and split learning approaches work on horizontally or vertically partitioned data and cannot handle sequentially partitioned data where segments of multiple segment sequential data are distributed across clients. To overcome these limitations, we present a novel federated split learning framework, we call it as FedSL, to train models on distributed sequential data. The most common machine learning model to train on sequential data are, as we know, recurrent neural networks. Since the proposed framework is privacy preserving, segments of multiple segment sequential data cannot be shared between clients or between clients and the server. To circumvent this limitation, we propose a novel split learning approach tailored for recurrent neural networks. And we integrate, therefore, we integrate split learning in recurrent neural networks with a federated learning kind of framework. So in FedSL, none of the data or label or complete model parameters are shared between clients or between clients and server. Only split subnetworks are shared between client and between clients and server. Now, to give you more detail, I invite Dr. Ali to present rest of the presentation. Thank you very much.
Okay, thank you, Shahroz. Here again, we are seeing multiple segment sequential data XJ. XJ contains two segments. XJSK is the segment S available at client K. XJS plus 1L is the segment S plus 1 available at client L. We are going to train a recurrent neural network using this multiple segment sequential data. It is the unfolded version of a recurrent neural network. Each hidden state of this recurrent neural network is responsible for one time step of training sequence XJ. One segment of XJ is available at client K and another segment of XJ is available at client L. And we are not allowed to share segments between clients. So we split recurrent neural network from the dashed line. And we call this layer the split layer. In this way, we have two subnetworks. The left side subnetwork is at client K and the right side subnetwork is at client L. The left side subnetwork at client K using XJSK performs forward propagation and sends the activations of hidden state to client L. Client L having its own local training segment and also having label performs forward propagation and backward propagation and sends the gradient of loss with respect to the activations of hidden states to the client K. Client K performs backward propagation, and in this way both subnetworks perform forward and backward propagation and update their weights using their local training segments without sharing segments between each other. After explaining split learning in recurrent neural network, now we introduce our overall framework, which is federated split learning. It's a combination of federated learning and split learning in recurrent neural network. The process starts from server. Server initializes global subnetworks and sends the initialized global subnetworks to all clients. Again, we consider clients K and L containing two consecutive segments of a multiple segment sequential data. Client K, starting from the received initialized subnetwork, performs forward propagation and sends activations of split layers to client L. Client L performs forward and backward propagations and sends the gradient of loss to client K. Client K performs backward propagation. And in this way, client K and L, by communication with each other, update their weights and update their subnetworks. And all clients, after updating their subnetworks locally, send the locally updated subnetworks to the server. Server aggregates all locally updated subnetworks to generate global aggregated subnetworks, and server sends global aggregated subnetworks to all clients. And this process continues until convergence and until clients have new multiple segment sequential data. Here we can see the results of applying the proposed method to non-IID sequential MNIST dataset for training identity recurrent neural network. We compared the proposed federated split learning with federated averaging with segment sharing. The federated averaging method cannot handle multiple segment sequential data, and the segments should be shared between clients. As we can see here, The proposed method successfully trained model on multiple segment sequential data without segment sharing and achieves higher test accuracy in fewer rounds of communications. Here we can see the results of applying the proposed method to non-IID EICU dataset for training LSTM recurrent neural network. EICU dataset is a real-world multi-center electronic health record dataset. As we can see, the proposed federated split learning framework successfully trained models on multiple segment sequential data without segment sharing. So as we saw, federated split learning successfully trained recurrent neural networks on multiple segment sequential data and compared to the previous methods, splitting recurrent neural networks in federated split learning method results in a speed up in convergence and enhanced privacy. And these are the links to our paper and the link to the codes of implementation of our paper. Thank you so much.
Thank you for the talk. I see Ali is in the speaker Zoom call. So any questions will be posted on Slack. One quick question, if Ali is still around, is by segments, are you referring to also dealing with skip connections, or skip connections are not dealt with in this work or your paper? All right. Yeah, I think, yeah, there is some mismatch in the, yeah. Okay. So I guess. I hear some noise.
Hello.
Hello. Yeah.
No, we don't know. We don't do any skip connection here. We just consider multiple segments of a sequential data distributed between consecutive clients.
Got it. Got it. Okay. Yeah, it's interesting. Okay, very cool. Yeah, and other questions would be on Slack.
Thank you.
Now and following up. All right, so moving to the next research talk.
Hi, everyone. My name is Sheroz Khan. I'm a...
Okay. Okay, it's by myself with our collaborator in the university, jointly with Julia Bala and Ramesh Raskar. So the talk's about differentially private supervised manifold learning with some applications to private image retrieval. Hello, everyone. This is our work on differentially private supervised manifold learning for private image retrieval. I'm Praneeth Vepakama, and this is joint work with Julia Bala and Ramesh Raskar at MIT. This is the use case of interest that we consider. There is a client, there is a server. The client would like to retrieve nearest matches to its image query. The server holds a large database of images and serves back the results. The critical constraint that the client places on this process is that its image query is private. Therefore, the whole process needs to be performed on privatized representations. We call our approach private mail, and this is the slide showing the life cycle of how the system interacts with our private mail protocol. So this is the client's premise. It holds the private image query. It also holds some public data. The public data and the private image query are passed through a trained model that is specialized for image retrieval, such as CGD, for example. So upon this inference, it extracts features that are suitable for performing image retrieval tasks. Now these non-private features are passed through our private mail protocol that we share in later slides. The private mail privatizes these features on both the public data and the features that are obtained on the query. These privatized client data representations are sent now to the server's premise. The server, as I said, holds a large database of images, and it also uses the same public data because the public data is non-private. Now these images are passed through the trained model suitable for image retrieval, and upon this inference, it obtains non-private embeddings from the trained model. It also has the privatized representations of the client's data and image that were sent to the server. These two representations are aligned using a standard rigid alignment algorithm, and k-nearest neighbor matches are retrieved post the alignment. The retrieved matches from the database are sent back to the server. So before we get into the details of private mail, we show a non-private version of a fine-tuned embedding that is performed in a supervised sense using the features extracted from these image retrieval architectures. So this is an example embedding obtained on the Cub dataset of images. And as you see, as we perform multiple iterations of our proposed embedding, although this is still non-private, begins to preserve the class separation that is shown by the colors. And the equation that you show below is our proposed equation that we use to embed our data set in a non-private sense. Now we show a differentially private version of that equation that we could run in order to obtain similar embeddings that are supervised and also preserve class separation, while also making sure they're formally differentially private. The key part of the slide that I like to show is the one in the green box. The way differential privacy algorithms work in general is that for any given query, one needs to know what is known as the global sensitivity of that query. And typically the global sensitivity is never data dependent, and it is only dependent on the compute that the query does. So it doesn't depend on any specific data set. So we were successfully able to obtain the global sensitivity, a bound on the global sensitivity for the supervised manifold learning query that I showed you in the previous slide. Once we have this, we know, given the amount of privacy that one requests for differential privacy that is specified via epsilon, we know how much noise needs to be added in the final step once the embedding is obtained. So these are some real experiments on the Cub 200 dataset. On the top left here, we show the privatized versions of the embeddings, which are the ones that you see in the scattered form, which are the embeddings of the client's query datasets. And the more compact representation that you see here in the middle is the embedding which is non-private, that is obtained on the server's premise. And this is done for a choice of epsilon equal to 1. Note that the lower the epsilon, the higher the privacy you're asking for, and therefore more the noise that is added in a structured form. And of course, if you ask for way too much privacy, the noise would be way too high to maintain any reasonable utility. But typically, numbers that are around an epsilon of 1 are considered to be reasonably private. Now, on the top right, you see a similar output, but as you see, the scattered points, which are the privatized versions of the client queries, are very much in alignment with the compact version that you see in the middle, which belongs to the embeddings of the server. So in the bottom, we show again similar results with an epsilon equal to 5, which is somewhat lesser privacy, actually way lesser privacy than for epsilon equal to 1. And as you see here, the alignment is very tight, which means the utility is further increasing, but of course at a loss of privacy. So now we show some results of measuring the recall at 8 metric, which is typically the metric used in information retrieval. And we show on several data sets of CAR 196 and Cub 200 that even with reasonably practical values of epsilon, we achieve a reasonable accuracy, especially when we continue to run our iterations further along. A few other tricks that we use as part of our scheme is the fact that we perform the embedding in a private form, and then after a few iterations of our private embedding, we make sure that we rerun all the inputs to the next embedding in a way that the post-processing property would hold, which means once you add the noise and once you are able to achieve the post-processing property after some changes, you don't need to add any more noise after that. Any other operation that is performed after the post-processing step is still formally differentially private. So for further details on how we make that jump from a non-private supervised manifold learning algorithm that we propose to a differentially private version of that embedding, to some post-processing operations that we do, following which we are able to get this immutability from post-processing where we don't need to add any noise more. For further details on this, please check out our paper. Thank you.
All right, so yep, any questions and follow-up, we can do that on Slack. As we move along, we go to the next research talk.
Hello, everyone. This is our work on differentially private supervised.
Here, this is by Abhishek Singh, Ayush, Vivek, Ethan, Emily, myself, and Ramesh Oscar from our group and Harvard Medical School on DISCO, dynamic and invariant sensitive channel obfuscation at CVPR 2021.
Welcome everyone. This is a presentation on DISCO, dynamic and invariant sensitive channel obfuscation. So starting with the scope of this work, we are basically operating under the regime of split inference. Also, many papers have called private collaborative inference. The idea is simple. We want to perform distributed inference for multiple reasons. One could be privacy, the other could be model secrecy, and etc. But the underlying architecture is still distributed inference and not training. A majority of the privacy and distributed ML focus has been around training, but not inference. And hence, in this work, we focus on inference. More specifically, the goal is to take X, pass it through the client network, which is trusted, and produce Z, and send the Z to the server. However, we want to ensure two things. First is sensitive input reconstruction should be minimized as much as possible from Z to X, and also sensitive attribute prediction, which is basically taking Z and predicting some other Y hat, where Y hat is a sensitive variable. Like, given a face image, if the server's task is to classify gender, maybe it can be used to predict race. Now that we have said about the scope, let's go to related work. So this work can be broadly categorized or compared with 6 broad domains. The most important one here is private representation learning. The idea is to take a sample and produce a representation for that sample such that there is some notion of privacy there, and it doesn't have to be necessarily privacy as in differential privacy and other metrics conventional use of privacy. Here we are what we are considering here is sensitive information leakage. The other common field which is very relevant here to discuss is channel pruning, and as we will describe going further, that our method is leveraging channel pruning such that privacy sensitive information can be suppressed, and in order to enable that suppression we use channel pruning. Natural pre-image is an idea in image processing and also computer vision, where we take the activations from our neural network, try to reconstruct its, not reconstruct, but try to obtain its pre-image, which is basically sample. Given that there are many pre-images possible, what we want to obtain is the pre-images which are actually on the manifold of natural images. And as we will discuss further in this work, one of the attack model is built around natural pre-images. The fourth is also very close to private representation learning, what we are calling here as bias in machine learning. What we want to do in representation learning is create representations such that some of the attributes have been suppressed. Sometimes these attributes manifest themselves as biased attributes, and hence suppressing them enables fair machine learning. And there are much more rigorous notion of bias in machine learning, but we are not considering and just comparing it with our work. The fifth one is part-based representation learning. Here the idea is to segment images into multiple patches such that each patch represents a part of the image, and then we can learn representations on the parts instead of learning the representation on full images. And this has its own advantages. In our work, we use this idea to improve the privacy versus utility trade-off. The sixth one is filter generating network, and it's basically a secondary network to the main architecture such that we can project multiple filters, and these projections allow us to predict which filters are more useful than the others for the given task. So contribution of this work is basically introducing DISCO, which is a dynamic scheme for obfuscation of sensitive channels with the goal of protecting sensitive information. Also, we have introduced new attack schemes which allow us to reconstruct the inputs or predict attributes given the activations or the representation. The third contribution is essentially our proposed architecture, which allows a very good privacy utility trade-off and is able to beat state-of-the-art methods which try to do same thing across multiple data sets, more specifically Cypher10, Fairface, and Celebi. We also release benchmark for split inference with more than 1 million samples, where the benchmark is across 3 parameters. One is the attack scheme, the defense scheme, and the data set of activations as well as the images, such that any given inference can be performed. The goal of benchmark here is to enable a level ground for different defense and attack schemes, which we found lacking in the existing works, and not just the papers but also as a community, and hence we want to enable more fair comparisons and hence the benchmark. The threat model here is, as we discussed the split inference setting, we have a client network which is trusted, and then we have server network which is not trusted and hence can be thought of as a malicious interceptor of activation Z. It has access to leaked activation pairs. In that case, we basically train a supervised decoder to take the activation and reconstruct the image. However, the assumption of leaked activation pairs might not be practical in some scenarios, and hence we have the notion of leaked client model. In leaked client model, essentially we do not have any activation pair leaked for the training of decoder, but we have the weights of the client model, and just using those weights and the target query, we try to perform optimization in the image space, and hence we call it likelihood maximization attack. So this is the architecture for DISCO. Under this threat model, the whole processing happens on the trusted entity, and once the training is done, the whole infrastructure is deployed across client and servers. So on the client side, we have convolution feature maps, and one part of the feature map, as you can see here, goes to the generator. Not generator, but filter generating network. And from that, we obtain the mask for each channel, and the mask basically tells whether to enable or disable the channel. At the same time, we also take the convolution feature and basically perform the masking, and after that masking has been applied, we obtain feature maps. Now here, another important detail is that the image goes under multiple slits, and hence we achieve spatial segmentation of the image, as we were discussing in part-based representation learning. The next part is adversary network, where we have the adversary trying to predict the sensitive attribute, and the task network, which is trying to predict the utility attribute. Each of them have their own loss functions, and the loss is obtained on both, and then backpropagation is performed over the whole network. We ensure that the gradients do not flow to the convolution architecture here, because that would allow us to have transferable filter generating network, such that these convolution maps, which are the feature maps which are produced, do not carry any information about the adversary network. So the metrics we use in this whole work is around two aspects. One is on the utility side, and the other is information leakage. On information leakage side, we have sensitive attribute prediction accuracy. Going back to the example of race versus gender, where we want to predict gender but at the same time hide race. Here, the sensitive attribute would be race, and hence how well an adversary is able to perform is measured by the test error of the adversary in predicting the race given the representations. Then we have sensitive input reconstruction quality. Here, since it's an image, there is no direct metric to quantify the image quality, and hence we use different metrics like SSIM score, L1, L2 error, and PSNR between the reconstructed image and the actual image. On the utility side, we have standard machine learning metric, test error. But there are two more parameters here which are worth considering. One is pruning ratio. As we discussed, the whole point of this architecture or this method is to suppress some of the sensitive features by performing channel pruning, and hence pruning ratio allows us to dynamically adjust the privacy utility trade-off. The last metric we have here is split layer. As we know, the point at which client and the server network are split is also important, because the granularity of representation changes across the layer, and hence performing attacks, any kind of attack, gets more and more difficult as we go deeper in the layer. At the same time, it also creates a problem for the client, because now the computation cost and the computation load comes on the client if we let too many deep layers get processed on the client side. Here's our evaluation. As you can see, Disco is the most last row in this diagram. Each block represents a given block of the ResNet architecture. So we have 7 blocks here. The original image is on the first column. We compared with some of the methods used in the literature and some of the baselines we have produced ourselves, for example, random pruning. Here, as you can see, adding Gaussian noise more or less enables reconstruction even as we go very deep. However, for most of the other methods, as you start going deep, reconstructing the image gets more and more difficult. While Disco shows a very good performance in reconstruction starting from block 1. However, in evaluation 2, we also compare different methods across different samples. And on the left side, we have again the same reconstruction quality comparison, but on the right side, we have reconstruction quality comparison, but with different attack scheme. So the one on the left represents likelihood maximization, but on the right, it represents supervised decoder attack scheme. As you can see, even the Disco is able to leak some of the information, which allows reconstruction of the image, but at the same time, many of these images in this attack scheme do not really correspond to the ID of the person, because it's only able to reconstruct the pose and some of the facial features, but not a person who is identifiable from the face. At the same time, identifiability depends upon the attack model or the side information which the adversary has. Hence, we leave it as an open argument about the privacy aspect of it. So in summary, Disco is about 4 important terms here. Dynamic pruning mechanism. As you saw, the filter generating network itself is dynamic, and hence what to prune and what not to prune is decided upon the image itself. The I stands for invariance, because we are doing invariant representation learning with respect to sensitive attributes. S is for sensitive and C is for channel, because the whole point of this method is to identify sensitive channels using filter generating network. And then obfuscation. Once we have identified the sensitive channels, we can remove them, suppress them by performing obfuscation. And here we are using one particular method called pruning, because we know in the channel pruning literature that removing a lot of channels still allow us to get good utility, while at the same time removing some information. So with that, I would like to conclude and thanks the audience for listening to us.
All right, thank you, Abhishek. Yep, so the Slack is open for Q&A, and we'll be happy to respond to questions over there. So moving on to the next talk, it would be in the next slide. All right, so this one's from Xinyu Liang, Alireza Javed, Michael Skoglund, and Saika Chatterjee from KTH Stockholm, Sweden. They'll be talking on a low complexity decentralized NN with centralized equivalence using layer-wise learning.
Hello, my name is Xinyu Liang. I'm a PhD student from Division of Information Science and Engineering of KTH in Sweden. Today, I'd like to talk about our recent work, namely a low complexity decentralized neural net with centralized equivalence using layer-wise learning. This work is co-authored by my colleagues Alireza, Mikhail, and Sekat. First of all, I would like to introduce our main problem of interest. Let's consider some examples of network systems these days, like the blockchain network and the social network. There are more and more visible or invisible values lies in the data located around us. Is it possible to improve the local learning model performance by making usage of other data lies in other nodes in the network? The answer is yes. We are motivated and looking into the decentralized learning setup, which is also called data parallelism. Assuming a training dataset D, it is distributed in a communication network. This network is undirected and without any mastering node. So for a specific node M, it has its local data, XMTM, and this node M is only connected to a subset of the other nodes in the network, not necessarily all of them. And this node M has a local object function FM, and it only has direct access to information about this local objective. By collaborating with other nodes and exchange information and knowledge, the local performance can be improved. But because of social and legal risks caused by exposure of real data, it is not allowed to exchange the real data in the network system. So the goal is for all the nodes to collaborate with other nodes and exchange the model parameters to find and agree on a minimizer of the sum objective, which approximates the centralized performance as if all the data samples are available at a single node. So is it possible to realize such a centralized equivalent solution? The answer is maybe yes. When we look into this randomization-based deep neural network called self-size estimating feed-forward network. This is a multi-layer feed-forward neural network constructed in a layer-wise manner. In each layer, the model parameters are the hidden layer weights, RL and VQ. These two parameters are predefined and fixed matrices, especially RL is chosen randomly. They are predefined and will never updated in the following learning process. While L denotes the output of the nonlinearity in layer L when we feeding in input X into layer L. So it means in each layer, there is only one model parameter, output matrix OL needs to be learned. So we only solve one convex optimization problem to find the optimal solution for output matrix OL star. After OL star is obtained, we add one more layer after the current layer to construct a deeper neural network structure and making this learning process continue and repeat. So there are two advantages of SLDML comparing with other traditional ANNs using backpropagation. First is its fast training time because it's feed-forward structure. Second is its simplicity, as there is only one parameter need to be learned and there's no need to calculate the hidden layer weights. So we choose SLDML for realizing its decentralized setup for two reasons. First is its potential to find the global solution, also called the centralized equivalent solution, as each layer is only solving a separable convex optimization problem. The second reason is its feed-forward structure leads to a low computational complexity. So we realize this decentralized SLDML in these ways. We adding up all the local objectives to construct a new problem, and this problem can be solved using a method called alternate induction method of multipliers in a distributed manner to achieve the centralized performance. We adding a constraint by forcing every local output matrix OM equals to a global O in the end. After adding this constraint, this whole problem is equivalent to a centralized problem, as if all the data samples are available at a single node. And using ADML algorithm, we can solve this problem by first introducing an auxiliary variable z, and then after some multiplications, the ADML iterations for mth node results in these three steps. The second step is a Z update. It requires a parameter averaging over all the nodes in the network. And for achieving this, it requires a sufficient times of information broadcast and exchange of all the nodes in the network. To do this, each node will broadcast its local parameters and receive model parameters from its dark neighbors and do a neighborhood parameter averaging. After sufficient times of doing this, every node in the network are traversed. So for each node, it can has a parameter averaging over all the nodes in the network. So to conclude the technical conditions of decentralized SLDML for achieving a centralized solution, it can be only applied to an undirected communication network structure, and to guarantee the equivalent solution, ADML should take sufficient times of iteration to converge to the global solution. And in each iteration, it requires sufficient times of communication to obtain the network consensus. Usually, the total number of iterations is a small number, let's say within 100 iterations. And the last condition is the existence of a global clock. It means this algorithm requires synchronous communication. Means that every node should activate during the same time interval and wait until the slowest node finishes processing its local data. When all the nodes get the global solution O for a specific layer L, we can add another layer after this current layer to continue the learning process and repeat the distributed algorithm in this manner. To test our proposed decentralized SLDML, we applied the algorithm onto an undirected network topology called circular communication network. It can control the network connectivity by changing the network degree. So in each node of this network system, we fix the SLDML size, means that we fix the number of hidden neurons in each layer, and we fix the total number of layers for SLDML. And we predefine the random weights matrices RL and predefine BQ, and inform all of these parameters to all the nodes in the network. So in the end, every node in the network can learn the same SLDML structure. The first experiment is to compare the test accuracy between centralized SLDML and the decentralized SLDML. In the table, it shows that for every dataset, the test accuracy of decentralized SLDML equals to the centralized SLDML. For some datasets, we observe slightly higher test accuracy of decentralized SLDML. They are caused by early stopping issue. We observed this in the experiment, and we kept this as it is, since it is an advantage to both avoid overfitting problem and to reduce the training time. Another thing to mention here is the choices of hyperparameters, μs. They are the step sizes of ADML. Since they are non-sensitive, we just choose it doing one-time parameter tuning and fix it as it is. Comparing with the gradient descent step sizes, this one is much easier to tune and also reduce a lot of computational power. The second experiment is to see the behavior of the objective cost as the number of layers increases. For this experiment, we just want to show that the overall objective cost is decreasing and converging to and converges as the number of layers increases. So this results also duplicates the case of centralized case. The last experiment shows the behavior of the training time as we increase the network connectivity. When network degree equals to 1, it is a ring network. When it is equals to 10, it is a fully connected network. For both cases, the centralized solution are obtained. So the only difference is the training time. To conclude, because of the data security and the privacy issues, we propose this decentralized learning, which only exchange learning model parameters in network. And this learning algorithm reaches the same performance as the centralized case. Compared with ANNs using backpropagation, this decentralized S7 has less computational complexity in structure, and the use of ADMM reduces the computational power thanks to a much easier parameter tuning process. And with sufficient times of parameter exchanges, the algorithm can provide centralized performance for a network with a high sparsity level in its connections. And our future work would be to adapt this algorithm to a synchronous communication manner. And if this can be done, we can extend this algorithm to a more relaxed communication condition. So that's all for my presentation. Thank you for your attention. And you are very welcome to ask questions or leave comments.
Thank you very much. That was a very interesting talk. So we are moving along correctly on schedule. So the questions will keep coming on now and offline on the Slack channel. So the speaker will continue to respond there. Moving along to the next talk, we have Dario Pasquini and Giuseppe Antonius and Massimo Bernaschi from Sapienza University di Roma, Stevens Institute of Technology, and they're going to be talking about some attacks on split learning in the inference setup, unleashing the tiger inference attacks on split learning.
Hi everyone, my name is Dario from Sapienza University of Rome. And in this short presentation, I'm going to talk about our security analysis of split learning. This work has been done in collaboration with Stevens Institute of Technology, New Jersey, USA. In our work, we aimed to verify two main properties of split learning. The first is the security of split learning against a malicious server. That is, if a malicious server can or cannot infer meaningful information on the client's data during the training. The second property is the security of split learning against a malicious client. That is, if a malicious client who participates to the training can or cannot leak information on the data of the other honest clients. In the next few slides, we will see how split learning can be violated on both these adversarial scenarios. Let's start talking about the malicious server scenario. Here, the server is malicious and wants to recover the private training instances of clients from its mesh data. The server tries to do this during the training process, so while the clients are learning the distributed model. We assume that the attacker has no knowledge of the client's network F. It doesn't know anything about its weights. Here, the only assumption is that the server has a general knowledge on the distribution of the private training sets of clients. For instance, if the clients are training a face recognition model, the attacker knows that the client's training sets are composed of pictures of human faces. The core idea behind our attack is quite simple. The only thing we have to understand is that even if the server doesn't know anything about the client network F, the network F is trained using the gradient received from the server. Therefore, the server can force F to learn any function by just providing suitable gradient to it. In this direction, the server can force F to learn a function that leaks information about the raw input data that is used to cast the smash data sent during the training. For instance, the server can force the network F to learn a function that can be easily inverted. To carry out the attack, the malicious server uses three networks. The first two networks are used to build an autoencoder, which is trained with a dataset that follows a similar distribution to the client's private training sets. Here we can see f tilde as an encoder function that maps the data space into a feature space. In the same way, we can see the inverse of f tilde as a decoder that maps back the feature space into the original data space. Essentially, the decoder aims to force f tilde to learn a feature space that is invertible. Then there is a third network, D, that is a discriminator, which is trained to distinguish between the output of the client's network F and the output of the network F tilde. This network is then used to cast the gradient for the client's network F during the training and bring it in an insecure state. In particular, we use the discriminator D to implement an adversarial loss function for F. That is, we train F to fool the discriminator D. More pragmatically, we cast a gradient that trains F to produce an output that is indistinguishable from the one of F tilde, according to D. This slide should give a better intuition on the process. At the start of the attack, we have that F and F tilde map the data space into two different feature spaces. Then we use the discriminator to train F to produce an output that is as close as possible to the one of F tilde. After a certain number of iterations, the feature space learned by F overlaps with the one learned defined from F tilde. Once that this is happened, we can use the inverse of F tilde to map back the smash data sent by the client during the training and recover good approximation of the original private data. Here are some results. In our paper, we tested different image datasets. As can be observed, with this attack, a malicious server is capable of violating clients' privacy by producing good reconstructions of their private data at the instance level. This would allow the server to leak complete private sets by just inverting instance after instance. This server-side attack applies on almost all the variations of speed learning. For instance, it applies also in the U-shaped form of speed learning, the one with the private labels. Indeed, this attack can apply even if the client controls the computation of the loss function. Indeed, it's enough to ignore the gradient received from the second split of the client and perform the attack as we saw before. Similarly, it applies on other variations, for instance, on speed learning when the synchronization among the weights of the clients is made with Federated learning. And it applies also on vertical speed learning. Indeed, the core idea is that this attack remains applicable as long as the server controls the learning process of the clients. This happens always in speed learning. For similar reasons, this attack is also capable of evading defensive techniques such as the distance correlation minimization. For more details on this topic, please check our paper. Let's glance also the client-side attack. Here the attacker is one of the clients who are participating to the speed learning product. The attacker was to infer meaningful information over the private training sets of other honest clients that are participating to the training. This attack requires no assumptions. That is, the malicious client has no additional information on the private sets of other honest clients. However, in this case, we can trust the server. This attack is essentially an extension of the GAN-based attack devised for federated learning by Itachi et al. In particular, this attack works on the U-shaped form of split learning. Here, the malicious client trains a GAN generator to reproduce the distribution of a certain class owned by one or more honest clients. To train this generator G, the client uses the distributed model as a discriminator by just altering the computation of the loss function on the client side. However, being an adversarial loss, the malicious client must also avoid the server's network hash to modify its weights while training the generator. To accomplish this, the attacker resorts to a gradient scaling tree that reduces the magnitude of the gradient for S and prevents it to change its weights during the distributed backpropagation. Then, once received the gradient from the server, the attacker scales the gradient back and uses it to train the generator. Once that the generator G has been trained, the attacker can sample data points that follow the same distribution of the target class. This allows the attacker to leak information on the private sets of other honest clients. Thanks for your attention. Please check our paper for more details and additional results. Our code is available on GitHub. Forecast and try to extend or prevent our attacks. Thank you.
Thank you, Dario. That's a really good talk. I see Dario is in the speaker room. So there's a question on Slack from Chandra Thapa, CSIRO Data 61. How many layers are there at the client side in your testing that you did? And was there a test done on number of client-side layers versus the level of success of these attacks? So Dario, you might have to unmute. So I'm giving you the permission to do that on my dashboard.
Okay. Hi. We use a ResNet. Can you hear me, right?
Yes. Yeah. Go ahead.
Okay. It was a ResNet with at least 4 residual blocks. Inside each residual blocks, we have at least 2 convolutional layers. So it's about, I don't know, more than 50 layers. And yes, we test different number of layers in the attack. And there is a very small difference between the results. Yeah.
Very cool. Very cool. All right. So moving on to the next slide. This is the last research talk of the day. And after this, we would have I believe, a break and then a coding session where Abhishek is going to give you a hands-on coding workshop. So this one is from Liao Xianga, Hao Zhanga, Hao Xian, Ma Yifan, Zhanga, Ji Reina, and Quan Shi Zhang from Shanghai Jiaotong University, South China University of Technology on interpretable complex value neural networks for privacy protection.
Hello, everyone. Today, I'm going to introduce complex valued neural networks for privacy protection. Previous studies have found that adversary attackers can extract input information from intermediate layer features. In this paper, we study the possibility of boosting the difficulty of such attack. Therefore, we propose a set of rules to transform traditional neural networks to complex valued neural networks. Intermediate layer features in your networks are complex valued, but all parameters of complex valued neural networks are still real numbers. Our basic idea is to hide the input information into a randomly selected phase of complex valued features. The target phase can be considered as the key for the encryption. Without the target phase, the attacker cannot extract the original input information, even if the attacker can get the intermediate layer feature and parameters of the neural network. As for the user with the target phase, they can easily decrypt the feature and recover the output from the encrypted features. Here, we provide a more detailed architecture of the complex valued neural network. The network consists of 3 modules, including an encoder module, a processing module, and a decoder module. The encoder extracts intermediate layer features from inputs and turns a real valued feature into a complex valued feature. Then, the encoder encrypts the complex valued feature by hiding the input information in a specific phase. The encrypted complex valued feature will be sent to the processing module. The processing module further processes the feature without changing the phase that hides the input information. The decoder decrypts the processed feature back to a real valued feature and gets the final result. The encoder and the decoder are embedded inside a local device, and the processing module is located at the public computation center. In order to enable successful encryption and decryption, the processing module needs to satisfy the rotation equivalence property. We propose a set of generic rules to revise the operation of each layer in the processing module to ensure the rotation equivalence property. For example, for the convolutional layer, we remove the bias term. For dropout layers, we randomly drop out both the real and imaginary parts of complex valued features to ensure the rotation equivalence property. Please see our paper for more discussions about the revision of each layer. In this way, the rotation equivalence property of the processing module can be recursively guaranteed. In order to further boost the difficulty of hacking the input information, we use adversarial learning to train the encoder. An ideal encoder requires the encrypted feature contains sufficient information to cause obfuscation with the real feature. Besides, the encrypted feature and the real feature follow the same distribution, so that it is hard to distinguish which one is the real one. That is, attackers cannot distinguish which phase contains the input information. The overall loss of learning is formulated as follows, which contains the adversarial loss and a loss for the target task. In experiments, we designed 2 types of attacks to test our method. First, we used intermediate layer features to reconstruct the original input, that is, the feature inversion attack. Besides the complex valued neural network, we designed the following 3 baselines for compression. Note that we also divided the baseline neural network into the encoder module, the processing module, and the decoder module, which was same as the complex valued neural network. The first baseline was the original neural network without any revisions. The second baseline was the neural network with noises. We injected noise right after the encoder module, and the noisy feature was fed into the processing module. The third baseline was the network with additional layers. Since the encoder of complex valued neural network is based on generative adversarial network, we designed a baseline with the same structure of the complex valued neural network for fair compression. Here, we visualize reconstruction results of different networks. The last two rows, that is, images within the red box, are images reconstructed by features of complex valued neural networks. In the last row of syllaba, we cannot identify the person in the reconstructed images. Compared with reconstructed images of other baselines, attackers cannot effectively reconstruct inputs using features from complex valued neural networks. Here, we provide more quantification results of feature inversion attack. We find that complex valued neural networks have similar performance as traditional DNNs, but exhibit better performance in privacy protection. Furthermore, we tested the failure rate of reconstructed images from different networks. We have 5 human annotators to recognize the object in a group of reconstructed images. The results show that most annotators fail to recognize the reconstruction from the complex valued neural networks, which demonstrated the privacy performance of our network outperformed other baselines in the feature inversion attack. Another type of attacks is the property inference attack. As the figure shows, the property inference attack uses intermediate layer features to infer some sensitive input properties. For example, if we train a neural network for the age recognition task, attackers can extract intermediate layer features and train another network to infer other provide properties, such as the gender. We designed various types of property inference attacks. Curves in this figure provide the inference performance of different types of inference attacks. We observed that the error rate of the inference attack on the complex valued neural networks was significantly higher than other baselines, and was close to the random selection. Here, we provide more quantification results. We found that error rates of inference attack on complex valued neural networks were close to random selection on the CIFAR 100 dataset. Thus, complex valued neural networks diminished the attacker's power in inferring input-sensitive properties and outperformed the baseline network. In conclusion, we propose a generic method to revise traditional neural networks into complex valued neural networks for privacy protection. The input information can be hidden in a random phase of complex valued features. Experiments show that complex valued neural networks can effectively boost the difficulty of hacking input information. Please read our paper for more details. Thank you.
All right. Yeah, this is a really interesting talk where they're working in the complex domain and then trying to do rotation to obfuscate by having a similar amount of magnitude on the complex domain in terms of the real value of the data. So unfortunately, it's a very early morning in Shanghai in China. So the Q&A for this talk should be taken up in Slack, and they're going to respond once it's a better time for them. So this brings us to the end of the session for today in terms of the talks and keynotes. The next thing we have is a break, following which we'd have a hands-on training workshop on Courier split learning. The module 1 would be done today. So there is about a 10-minute extra time that we have, which is great. So our break would be longer by 10 minutes. And as you see, the schedule time for the training module begins at 3:50. So we have a 30-minute break, 20 minutes more than what we expected. So see everyone at 3:50, and we're going to share screen with our code, and also share our code with you so that it's already a frozen notebook so that you can already start running with it. Right, welcome back, everyone. So it's a hands-on training workshop, Code Your Split Learning, Module 1. I'll let Abhishek Singh share his screen and carry on the workshop.
Hey, everyone. Thanks for joining. We'll be doing a hands-on session for split learning. The goal is to go sequentially from a very simplistic setup to advanced. So I'll be sharing my screen and sharing the notebook as well. So you must have seen the notebook link on the Slack channel, and maybe I can share on the Zoom also, but I think most of the people do have access to it on the Slack. Let's see. So this is part 1, and we'll be soon jumping to part 2. And part 1 is more about introduction to split learning, and then we'll be talking about different kind of information leakage and corresponding threat models for split learning. All right, so I've shared the link on the Zoom as well. And of course, feel free to interrupt me on Zoom or preferably on the Slack, and I can answer the questions. So here's the scope for the tutorial part 1. We'll be starting with understanding the high-level idea for split learning and then setting up the training pipeline. Then we'll be going more into the weeds and discuss distributed forward and backward pass. And the last part would be scaling to multiple clients and simulating a distributed setup of split learning. So we'll start with the basic question, and most probably you know the answer already if you have been attending the conference so far. So what is split learning? It's a technique for distributed training and prediction without sharing raw data. And the very simplistic idea here is to basically take a neural network architecture, split it into 2 parts, such that first part can be executed by a trusted client, and the output of first part is then sent to the second part, which is typically executed on the server. Now, the advantage of this whole splitting the neural network is that client can perform some partial amount of computation, and performing that partial amount of computation saves the client from sending the raw data directly. Instead, it shares the activation. Also, a quick disclaimer. So this whole tutorial is designed for explainability, and you might find some of the code not optimized optimization in general, because the goal is to make sure that every person gets to learn something out of it and not basically get state-of-the-art performance. So we'll start with setting the runtime as GPU. And assuming that you have set up the Google Colab and you have the access to the notebook already, you can go to runtime. Then you can go to change runtime type, and you will see hardware accelerator as GPU, and just save it. In my, it already shows GPU, so I don't have to change it, but it might, in your case, it might be showing something else, so change it to GPU. Also, since the notebook has been shared from my Google account, you might get a warning. So just click run anyway, there's no danger here. We are just doing a tutorial. And okay, so let's load some libraries. We'll be using PyTorch library throughout this series. The goal is to use high-level APIs available from PyTorch and not go into the depth of the implementation aspects of it. And you can execute each and every cell if you're new to Google Colab by pressing Shift and Enter together. And then in the next line, we are setting the device as CUDA so that we can utilize the GPU in the future. The third cell here right now is about loading the data set. And we are using the data set called Cypher10. It's a data set of natural images, and it has 50,000 training images and 10,000 tests. It has images of natural classes like plane, deer, car, and categories like vehicles and animals. So basically, we are setting up our training data pipeline here. So we'll run this cell. Right now, it's downloading the data set because we have enabled download equals to true in our Torch Vision API, which is allowing us to download the data set. Now the data set is downloaded and extracted, and I'm hoping same has happened for you also. If not, then please feel free to ask any question on the Slack. So, okay, going back again to split learning setup. here we have a single client and we have a single server. The way whole training operates is we take a sample X, we pass it to the client network, we obtain intermediate activations, we represent them as Z, then Z is sent to the server network, and finally prediction happens. Now this is the forward pass. When we send the Z is sent across the communication channel. It's not happening on the same device anymore because we are operating under a distributed learning setup. However, here to simulate such a setup, we are doing this whole operation on the same device. So that's forward pass. But as we know in deep learning, in neural networks, we perform backpropagation. So in order to perform backpropagation, first server network computes the loss, computes the gradients, and then sends the gradient of the loss with respect to Z to the client network. And then client network can perform remaining of the backpropagation. So that's the architecture as you can see on the screen right now. So we'll just initialize our client. Another detail here is that we are using PyTorch API. So we are using base class of n-indet module that easily allows us to create PyTorch models and perform training, inference, and all the things we want to do in general with neural networks. We have another hyperparameter here called cut layer. So again, going back to this diagram, the splitting of the neural network could have happened anywhere. So if we split at any given position, we call it cut layer. And the way this whole training will work is that there are gonna be some trade-offs depending upon what we choose as cut layer. For example, if my cut layer is very close to the final output, then majority of the layers are being executed on the client side. And similarly, if my cut layer is close to the input, then majority of the computation is happening on the server side. So that's that. Another thing here is we are using ResNet-18 as our model. It's a well-known CNN architecture, and we are using Torch Vision API to load it directly. And what we do here is we take the ResNet-18, we deconstruct its layers as stack. And then what we do is we execute each and every layer. And for technical correctness, it's not layer, it's a ResNet block. And each ResNet block consists of few layers. So we iterate over those layers, and then we check whenever we encounter the cut layer, we break from it and send the output to the server. So let's define our class for ResNet-18. The second part is defining the server architecture. So again, this diagram, we are not going to define the green part of the module. Here again, we are using Torch Vision API, ResNet-18. Another parameter here is the logits. So as I told before, we are using Cypher10 dataset, which means we will be doing prediction over 10 classes, and hence we'll be passing 10 as the argument for the logits here. And in the forward function, we have cut layer again defined, but this time because it's server, we execute the neural network only when we encounter the cut layer and start executing from there onwards. So that's that. Let's define the class. Another detail, if you're not familiar with PyTorch, so the forward function here gets called when the neural network is actually executed. So we'll be using the forward function later, but the initializer, the constructor in it is being used to define all the parameters of the model. So here we are, we choose the cut layer as 3 and the logits is 10 because we are using Cypher10 dataset. We define the client model, server model here. So now the models are initialized. Taking a bit of time here. Anyway, meanwhile, we have optimizer. So in order to train the neural network, we need to define loss function. And here we are using cross entropy loss as the criteria. And then we have client model parameters and server model parameters. And for each those group of parameters, we have separate optimizer. So we will set up the optimizers, and now the part comes for the training pipeline. So again, going back to this diagram, what we want to do is in our training pipeline, go from X to Z, then Z to Y, and that becomes a forward pass. And then during the backward pass, we are going to go back from loss over Y, then gradients with respect on the Z's, and then going to the gradients for the client network parameters. So that's what we have here. We have total number of epochs because we have to train it multiple times. We have the train loader, which means the raw data will be obtained by the client, executed on the client model, as you can see here. And then we take the activations, we set them as server inputs. You might be wondering, why are we using detach function here? The reason to use detach is because we are simulating the distributed learning setup and not really doing the full end-to-end distributed learning. We are using detach function to make sure that PyTorch does not actually calculate the gradients on its own. So we do the detach, and then that detached activations become the input to the server. And as you can see here, it goes to the server model. We compute the loss. Then server optimizes for the loss and computes the gradient. And I would say in this whole loop, this is the most important part, this line. So the client which had produced the activations now has to perform backward. Until and unless it receives the gradients from the server, it cannot. And hence, we compute activations.backward by passing gradient of the server inputs. So that way, the backpropagation happens for the client also. So we'll start the training here. And you will see the loss decreasing. And one thing here is that we are gonna stop it early because, of course, training on Cypher 10 till convergence takes a lot of time, especially on a single GPU. So we will be just seeing a basic trend in the fact that loss is decreasing, and then we will terminate the training and then go towards the next part just to make sure that we are on speed. But feel free to shoot any questions while the training is happening right now. Another thing I should mention here in this whole pipeline is that we are using train loader for the client, but in a distributed learning setup where the client network and server network are actually distributed across different systems, the server won't be able to see the train loader because that was the initial point behind split learning, that the client should not be able to aggregate data and send it to the server because then they're sharing raw data and there are concerns about privacy, information leakage, and so on. So as you can see, the training is going on and it's a standard Cypher 10 training. So you can continue it or also stop it if you want to go to the next cells.
Yeah, I think there is some questions on Slack. Do you want me to relay it or do you have a window?
Yes, that would be great.
Okay, yeah. So yeah, do you also plan to show how to prevent reconstruction of raw data from activations that the server receives? And,
yes.
Yeah.
Sorry, did I interrupt you?
No, go ahead.
So yeah, that's the second part. So basically, I'm setting up the base level for split learning right now. And the next part would be actually to understand the information leakage and how much reconstruction is possible.
Sure. One more question I'm getting. Let me see. Can you use the same optimizer across client and server? And how does this choice of optimizer and its parameters being different or same across client and server impact the process, and what is correct and what is wrong?
So we cannot use same optimizer for the client and server because in the real world setting, they are separated by geographical boundary and also from the communication standpoint. So optimizer on the client side will be initialized on the client device, and then the optimizer for the server will be initialized on the server side, and hence they'll be using their own optimizers. But the next question is more interesting, which is, can we use different optimizers? I think answer is yes. but it's also more about what hyperparameters do you choose and what kind of learning you want to perform. Typically in neural networks, we use same optimizer for the whole neural network. So you might want to use the same optimizer, but not just optimizer, but also learning rate. And if there are other hyperparameters like momentum and other things, depending upon what optimizer it is. So yeah, answer in short is yes, you can use different hyperparameters. But yeah, I think in general with a neural network, it's more or less about hyperparameter tuning. So you might want to start with something people have tried already, which is same learning rate and everything. Cool. So I guess we can wait till 20 epochs and then we can continue towards next modules. As you can see here, while the training is happening, what we will be doing next is basically save the models so that you can use it in future and you can download it because Google Colab session gets expired very soon. So if you want to play it with later, you can download it, and also we'll be computing test test accuracy. And then we'll be talking about how to scale to multiple clients. So let's see, where are we right now? 17, 18, okay. All right. So I guess we can stop the training here because in the end, it's just improving the accuracy by some margin. So let's create the directory for saved models. What's this? Oh, it's hash. So 1 second. Guess we can use OS API. All right. So what we're going to do is save the models. And remember that we have two models. So one is the client model and the other is server. And the way to save in PyTorch is basically load the weights using state dictionary API and then basically call torch.save. Now the next step here is to measure the accuracy. And the reason to do that is basically we want to see how much convergences happen. And typically Cypher 10 goes around something around 95, but since we have stopped it way too early, let's see what it is. So it's 69.61. If you want to get a better accuracy, you can continue the training. But since we want to cover the other parts, we'll be stopping it here. All right, so the next part is about scaling to multiple clients. So now in this split learning setting, we have a server network and client network, which we had discussed before. But there's another aspect to it here. We have multiple clients, and each client wants to learn a representation such that it can build an effective ML model. So the simplistic version for split learning for multiple clients is based on the round robin protocol, where the client number one starts with the training, then sends its activations to the server, server does the computation, server returns back the gradients, and the whole training pipeline happens. Once one epoch of training is finished, the client sends the weight to the next client. So as you can see in the diagram, from client number one, we go to the client number two. Once a single epoch is finished, then from client number two, we go to client number three and so on. And once we reach the final client, we go back again to the client number one. So that's why it's round robin protocol. And whenever each client is active during the training, they are essentially communicating the activations of the gradients only for one epoch. And again, just to be clear, it's the simplistic version. We have more sophisticated version where you can make the clients and the server more asynchronous. Also, another thing is that each client can share the weights to the next client, or cannot, or does not want to share, then it can avoid sharing the weights. It just changes the protocol. And there are two ways of sharing the weights proposed in the first paper for split learning. One is to share the weights among the clients by having clients talk to each other. But as you can imagine, in some applications that might not be feasible if the client devices are, for example, mobile phones or IoT devices. So in such cases, what happens is the client network establishes a secure channel through the server, and then client sends the weight to the server, and server sends the weight to the next client. So that way, server operates the whole client transfer protocol. So yeah, we'll initialize the 10 clients and basically perform the training. So if you remember, we had single ResNet 18 client last time, but this time we have to define 10. As we have kept the number of clients as 10, we will be initializing 10 different clients, and also we'll be initializing 10 different optimizers for each and every client. The way we do that is we iterate through the list of client models, take the parameters, and initialize a new optimizer. And of course, server remains the same server. So same single server optimizer. Okay, so we'll be setting up training pipeline for multiple clients like we did before. However, there is a key difference here, which is basically happening in this part of lines. And what is basically happening here is that at any given time, there is a single client which is active, and this happens across the loop. And whichever client is the active client, that particular active client gets the weight from the previous client and makes it its own weight. So that way you can imagine that training from the server's perspective is not changing at all, because whichever client is active had the most latest version of the weights. Another interesting thing to consider here is that for simplistic version of split learning, we are using the same train loader. However, all clients have their own data source, and they will be using a different train loaders for their training. But again, for the sake of explanation here, we are using a single train loader. So yeah, it's just an illustration. So each client can have its own train loader and then perform the training. The remaining lines are exactly the same as what we saw in the previous single client and single server setting. So we have activations from the client and server inputs and so on. So what we are going to do is basically start the training for the client. And you can see which client is active right now, which is 0. So we are starting the counting from 0 and going till n-1. And the loss is changing as different clients get their own turn. Also, as you can see the log, when the client which is active becomes 1, it loads the weight from the 0th client, because that was the reason we wanted to make sure that the weights used by the client are the most recent version of the weights. So again, like previous example, the training will continue. One thing here to consider is when we are doing multiple rounds of training across multiple number of clients, the training will get over with the last client. So it's the last client who has the most recent versions of the weight. Remaining clients can request for the weights, or remaining clients can use their own weights, because typically we train these models for convergence. And if the model has converged, then more or less these weights will be very close to each other, but at the same time, it totally depends upon the infrastructure, and if the client wants to request the final weights, they can. So yeah, we have the logs, which are more or less self-explanatory. It's changing the client every time it finishes one epoch. Right now it's still on the 0th epoch, but it has gone till client 6. Are there any new questions? Okay, so if you are also executing with me in parallel, you can let it run, but also we'll be again stopping it even though it has not converged yet because we want to cover other parts. In terms of future directions, this was a very basic introduction to split learning. So one thing you could wonder is how to make this round robin protocol asynchronous, because right now, whenever a single client is executing, all other clients are waiting idle. And maybe we can utilize that empty computation phase and do some computation on the client side such that each and every client is utilizing resources more effectively. Not just that, you could also enable multiple server scenario where there are multiple servers and they are talking to multiple clients such that we can leverage the high amount of compute infrastructure which is available on the server side typically, especially in the cloud computing scenarios where you have the horizontal scaling setup, basically. Another very interesting direction could be to basically simulate the setup where data distribution is different across the clients, and then try to see what all methods can we build such that these clients still converge across the distributed training setup. And there are more works around like different topologies of a client model. Like there are two kind of heterogeneity which can happen. One heterogeneity is the compute infrastructure. So one client can be a mobile device, the other client can be a GPU. The other heterogeneity is the topology in which clients are aligned with each other. So I think in some of the talks previously, boomerang split learning was mentioned, where even the label privacy is protected by protected to a certain extent by building a client which sends the data to server, and then final label is computed on the client again. So there are different variants and different topologies which can be tried out.
Yeah, so there is a question.
Mm-hmm.
Yeah, okay, yeah. So do you refresh the gradients or reinitialize them or anything of that sort during the training?
Sorry, could you repeat? I missed it.
Are the gradients reinitialized during the training or?
Yes. So whenever we perform one pass of backprop, we call this function client optimizer.0grad server optimizer.0grad. What it does is basically takes the parameters of the model and turns the gradient with respect to them 0, so that when we compute the next loss, the gradients again are refreshed with the most recent gradients.
Cool. Yeah, there might be one more similar point to point out, which can be tricky sometimes for the first-time user. Anything to keep in mind from code perspective when you're transferring the activations from the client to the server, and are there multiple ways to do it?
Yes. So we are operating in this simple setting where we call detach and create the server input from the activations, and then the server model receives the server activation. Sorry, client activation. Oh, sorry, was that the point, Praneeth, you were mentioning?
Yeah, that's it. Yeah. Let me check Slack. Yeah, this is great. So what is your plan for the adversarial, or like the reconstruction and the security, the attacks and defenses for split learning?
Yeah, so we have the notebook ready. So if you want to do it right now, we can start, or what do you suggest?
Okay, so yeah, we're reasonably okay on schedule. So we are
Okay.
10 minutes ahead, and there is no break scheduled anyway. So because we're just out of the break, so I'd say we continue the flow, and then we're done with the module 2. We can end 10 minutes early if that's what happens.
Okay, awesome. So if you're training in parallel with me, you can continue running it, but I'm gonna stop because It's still on the epoch 2. So we have a lot more epochs to complete. And we will jump to the next notebook, which is part 2. So I think I've not shared the, let's see. Let me share the notebook with everyone on Slack. Praneeth, can you verify the notebook can be accessed?
Yeah, let me see. Yeah, this is public, but the thing is, I think you gave me access beforehand. So.
Oh, this is a copy, I think.
Okay, so then yeah, then I can see. I can still verify.
Okay, you can access it, right?
Yeah.
Perfect. But yeah, of course, please ping on Slack if it's not accessible. All right, so here we start going into more details for split learning. So previous part was a tutorial to the introduction, but now we'll be trying to understand the information flow and what kind of threat models we can construct given the information available from split learning setup. Then the third part would be reconstructing input from the activation, like what all methods are there for reconstructing input. And then finally, we'll be setting up an attack pipeline and seeing how much reconstruction is possible. Okay, so let's make sure the runtime is selected as GPU. In my case, it is. Actually, let me run the main file only. So runtime, GPU, cool. So again, like previous setup, we'll be dealing with a single client and single server setup, because multiple client was more for illustration of distributed training setup, but here the focus is on single client and what all information can be reconstructed from the activations. So we will load libraries required for Torch APIs and also for some visualization, then setting up device as CUDA. And again, we are using Cypher10 dataset like previous tutorial. So this should be downloading it again. All right. Again, we define same ResNet 18 client, ResNet 18 server. And this time we are using cut layer as 5. So if you remember for ResNet 18, when we call model.children, we get multiple stacks of ResNet blocks. And these ResNet blocks are basically becoming where we define the split. So let's initialize the client model, server model. Also, since I'm skipping some details here because I already covered it in the previous tutorial, please feel free to interrupt anywhere if you find it confusing or there is any doubt. Again, like previous tutorial, set up the optimizer, and we will run the same training pipeline again like previous tutorial again. This time we won't be running a lot of epochs because what we are interested in learning is that given the activation Z, what you can estimate about the raw input X. So far, nothing new has happened. It's just the more or less replica of previous tutorial. But the next part comes where we try to understand different aspects of it. So maybe we'll train till 10 epochs and then go to the next part. What coming next is information flow. Since it's training right now, I will just quickly give a glimpse to what we mean by information flow here. So of course, it's an abstract term and you could mean multiple things out of it. But if you remember the architecture we had used in the first example, we take the input X, we pass it through the client network and obtain Z. And from the Z, we get to know the X. We try to estimate the X. And the question is around 2 points. One is how much information can you extract about X from Z? And also how much this information extraction capability changes as we change the cut layer across Z. So as you can see in the diagram briefly, like there is some dimensionality reduction happening as we go deeper in the layer, because finally we are ending up with a vector, which is output of the server network, and we are calling it Y. Since this dimensionality reduction is happening, and also there is some processing happening at each layer, as we go deep and deep, we should expect some loss of information because of the computation happening on top of X. And that's what we will be visualizing in the next part. Okay, epoch number 7. Maybe we can stop it here. So just for the sake of measuring tested performance, let's see what it is. It is 65%. You can train it more if you want, and you can get good accuracy. But we'll be focusing more on the role between X and Z and not much about Y. So first thing we are going to do to visualize the activation is load the training data set, load the training data loader, and then get one batch of images and labels. And now what I'm going to show is, let me actually execute it once more, is basically this. So Cypher 10, if you remember, has 2 broad categories. One is for vehicles, the other is for images, the other is for animals. And that's what you see in the original image. So I think it's an airplane, it's a frog, and so on. Now, these images are being passed into a CNN architecture, and then we get channels. And then in the next part of loop, I'm visualizing those channels. So another interesting thing here is that even in the Resonate 18, the first block outputs 64 channels. So of course, we cannot visualize 64 channels. So what I'm doing in the code is this. We take the client model, we pass it through the layer position, which is basically the split layer. And then I randomly sample a channel and visualize that particular channel instead of visualizing all channels, because then it becomes more cluttered. So this is what you see. This is what a neural network sees after passing an image from layer number 1, block number 1. Then this is what happens after passing it from block number 2, then block number 3, and so on. You might notice some trend here, which is as we go deep down, the information is becoming more and more coarse. And this is also somewhat conventional idea in representation learning as such, that as we go deep down the layers, we start with a very fine-grained filters like edge detection and so on. And by the time we are close to the ending layers, what we are detecting is like semantic concepts of high-level information. So eyes, nose, and faces, the body of the vehicle, so on, is being detected in the later layers. And this can be seen a bit in the information which is being visualized here. Another thing you could do here is for the experimentation, you can rerun the cells multiple times, because each time it is a different channel number because it's being sampled randomly. So let's see what's visualized this time. So as you can see, different information is encoded across different channels. So each time you run the cell, you will see different kind of grayscale images. You can also do some channel indexing. For example, we can make it RGB, although it's not an RGB, it's much more channels. So we can start with the third channel and essentially generate more activations. So this way you get a little bit of more information, although it's not really an RGB image because we just sampled 3 consequent channels. But you can still see some information about the frog in the images going down. So anyway, that's that. Another quick thing, if you did not follow, so the way we are obtaining the output of different split layer is by calling the client model.model API. And as you had seen in the ResNet 18 client definition, we are going layer by layer. So every time we get the module list, we can change the index of the list to get different layers output. So this is what is happening when I'm calling model and then treating it as a list in Python. So, okay, we can go to the next part, unless there is some question here. All right, so now that we have seen what kind of information roughly flows in the channels of an image passed through a neural network, we might want to construct a threat model out of it. So starting with the first part, which is the server can act maliciously, and the server can have access to either of these two things. First is a data set of pair of activations and input samples. So what would happen here is that we take the X, we take the Z, and generate lots of such corresponding data set, and then leak that information to an adversary. But sometimes that kind of leakage might not be practical because the clients are trusted. And in such cases, just knowing the client network's weight might also be sufficient enough to reconstruct a given Z towards X. So of course, this is a very, very specific threat model here. There could be many more threat models, and also just for the sake of technical correctness, it's not a formal definition of threat model. So that would require usage of much more jargon. So I'm keeping it much more explainable here. Another thing to consider here is, although we are talking about split learning, this is referring to the scenario of inference more than training, because in training, the malicious server is also talking back to the client by sending the gradients, and it can inject some information in the gradient such that the leakage is even more. So what we are talking about here is that given neural network architecture and every layer is frozen, no training is happening, how much information Z carries about the X. So now that we have defined the architecture to a certain degree, one of the attacker's goal could be to reconstruct the input sample, as we had discussed before, or it could also predict a sensitive attribute. So I think in one of the talk, we had referred to this example of race versus gender, where you have a gender classifier on the server side, but just by looking at the activations, it could infer multiple things, not just gender, things like race or multiple sensitive attributes. Then the other case is membership inference, where you want to get some confidence score about the given sample belonging to a given class, given a class of samples. So here we'll be focusing on reconstructing the input given the Z's. And this is how we basically perform this information leakage. So we take the trusted network. We take the trusted network, we send the Z's, but then the adversary trains a decoder such that it can reconstruct the input. So the adversary here is getting the Z, but it's training its convolution architecture to minimize the distance with respect to the input image and the reconstructed image. And again, you might wonder, how is he getting the access to input images? So that's our premise, that there is some leakage of information already happened. And during the testing phase, we want to see, given a new Z, how well he can reconstruct the input. Again, feel free to shoot any questions on this.
So there's a quick question.
Mm-hmm.
Do you also assume the adversary knows the labels or not?
In this case, not necessarily. Although the knowledge of labels might act as an extra piece of information, so it might improve in might allow better reconstruction.
Sure.
But the attack we are going to perform right now does not take that label into account.
Sure.
Mm-hmm. Okay, so what we have here is the server. And again, since the server is untrusted, we can imagine the server to be the untrusted entity, or sorry, the adversary. Or it could be also an interceptor of the Z's, even before the Z is fed to the server network for utility. And what we are going to do is basically build a generative model, which is also our convolution decoder, which will take the sample Z and learn to generate the images. And if you have seen these generative models before, feel free to skip. But we again define a ResNet block. But this time it's it uses basically different kind of convolution filters rather than standard, because we are trying to upsample the image rather than downsample. So this is the architecture for the adversary model defined here. And what we are going to do is basically build some layers such that the quality of the generated image is as high as possible. And usually one thing we have learned in generative modeling is that it requires a good and big architecture on the generative decoder side. So that's what we are doing here. And one of the most important building block here is transpose convolutions. So transpose convolution allows us to learn upsampling filters such that more or less information is preserved and also the right amount of information is added in the generative model. So without going into much detail of this generative architecture, we'll just execute it. And then we will set up the reconstruction training pipeline. Here we have adversary model and adversary optimizer. So we are going to assume that everything is now frozen. So client model is frozen, server model is frozen, although server model is not really useful here. So we won't be using it. We'll be taking the activation from the client and then basically learning an upsampling scheme, which allows us to reconstruct the image. So because we are simulating the attack scheme and it's not really a distributed ML setting. So again, like what we have done in the past so far, we get the activations, we perform the detach, and then we pass the server inputs to the adversary model, which tries to reconstruct using the reconstruction loss. So the reconstruction loss function here is L1 loss. And this is something we have seen working much better than other loss functions for reconstruction quality. But again, this is something very specific to the attack scheme as well as the kind of images we are reconstructing. So remaining thing is standard deep learning pipeline, optimizer, backprop, and everything. So another interesting point to be noted here is we are using model API. So as you can see, I have indexed the model with 1, which means the split layer is 1 right now. And that is just to illustrate that reconstruction of input is very well from the split layer 1. But if time permits, we can also see what happens if we go much deeper and then try to reconstruct. So with that, I will start the training.
So question again.
Mm-hmm.
So for the reconstruction, currently, is it required that the weights of the model are known, or it's just the activations for some attacks?
Yes. So I think, yeah, that's a broad question as such. So what we are dealing with is just activations, but it is possible that you only have the access to the weights, and you can utilize the knowledge of the weights to reconstruct the input. There are also attacks where you utilize the both aspects. You know some activation pairs, you also know client weights. So usually the more information you have, the better it is. And the better it is for attack, and the harder it is for to defend against the reconstruction. So in this particular example, we are considering the case where only activations are known. But just to simulate the setup, we know the weights, and that's how we are obtaining the activations.
Cool.
Mhm. So right now, the loss function, the loss statistic you're seeing here is specifically for reconstruction loss. So the fact that training loss is decreasing indicates that the decoder is able to reconstruct at least the training examples to a certain extent. We don't know yet how good or how bad they look, but the loss is decreasing is giving some indication in that sense. And again, I want to emphasize that we are using the most easy to attack scheme because the split layer is one. So it's literally single convolution layer and reconstruction from there. And in other words, what it means is that given this particular output, block number 1 channel, can we go back to the image? And what we are doing is we are taking a training data set of these two pairs, and then we will be testing it on the test data set and see how well it is able to reconstruct. So here, I think we might have to wait a bit more because we want to converge a little, because otherwise reconstruction might not look good if we stop it early. So we'll see how it goes.
So typically, what is the, oh, sorry, yeah, question, right? So typically, what is the size of the sample, number of samples that you're using to see reasonable quality?
Yeah, I think, yeah, that's a great question. And answer, I guess, belongs to the sample complexity of the neural network. So it's a generative model, and usually if it's a very low number of samples, then probably it's going to overfit. So reconstruction quality would be bad, but I guess, yeah, the right way to quantify it is sample complexity to get some estimate of sample complexity. But from an empirical standpoint, here we are using the whole training data set, which might be a bit too much. But again, as I said, for the sake of illustration, we are using the easiest attack scheme. Okay, so I guess we can stop at 17 epochs and see how the results look. So right now we are going to utilize the data loader from the test set. And there we go. All right, let's see the reconstruction results. So this is how, it's not fitting my screen. Yes, it is. So this is how the reconstruction looks. As you can see, more or less the image is getting reconstructed. I think, like, for example, this animal and this car is getting reconstructed to a certain extent. But it's worth noting that we had stopped the training quite early. So it's possible that the reconstruction quality would have been much better. And also this is test set, so the model is not really overfitting on the training images. So another thing here is that this whole reconstruction is happening from the information which was in the block number 1. So this grayscale image basically denotes the information which was used to reconstruct this sample. So now we can maybe try, and of course, if you are running the code in parallel, you can try different layers. So I'm just gonna run for, let's say, 5th block and see how's the reconstruction now. Okay, so probably some other, because our architecture for the generative model has to change. So now it's second convolution block, but remaining thing is the same. And it will be attempting to reconstruct information from the second convolution block. And ideally, as we go more and more deep, the reconstruction quality suffers more and more. And so yeah, that's pretty much it. If the training converges, we can visualize the results, otherwise not. But some of the future directions include, so yeah, some of the future directions are how to develop a better reconstruction model. So one thing we saw here is reconstruction was happening very nice. But if you get to run different layers, you will realize the reconstruction is not really great if the activation is coming from a much deeper layer. And then the question emerges, how can we still achieve good reconstruction? Because clearly, even a small dimension of activations is capable of encoding a lot of information. So going from the available information to upscaled image can be improved if we have a different generative architecture. So yeah, there may be more innovative methods to reconstruct it better. And I think the second question is more from a theory point of view, that what guarantees we can give about reconstruction, because if we can give some guarantees about reconstruction, then we don't have to ask that question number 1 much, because then we can say that this is the level of reconstruction which is possible, and you cannot bring a better model, at least under those guarantees, and get a better reconstruction. So it's like 1 and 2 are intertwined together. And the third would be that here reconstruction is more or less a harder attack because you're reconstructing the whole image, but there might be relatively easier attacks. For example, sensitive attribute prediction. So imagine just by looking at the activation, if you had to only predict, if the model had to only predict whether it is an animal or a vehicle, so basically a binary classifier, the problem becomes much more easier to solve rather than the reconstruction of the whole image. And that's what I mean here by sensitive attribute prediction, membership inference, and etc. So let's see how much epochs we have trained. Yeah, I think for the sake of illustration, we can pause it and see reconstruction quality from block 2. Another thing which I have not mentioned here, but I have encountered a lot during the experimentation with different layers, is whenever we apply max pooling or average pooling in the convolution architecture, the dimensionality of the channel reduces more, and reconstruction becomes relatively worse. Here, convolution block 2 does not perform any pooling, so the size of the channel is still the same. Anyway, let's see how's the reconstruction. And it looks to be pretty good. So even with the block 2, I think a good amount of information is visible, although as you can see, there is a good amount of blurring happening here also. So yeah, you can play with more parameters and so on. So tomorrow's tutorial is gonna be about defense mechanisms. As we saw, it seems to be easy to reconstruct the images given Z. So can we do anything on top of Z such that reconstruction of image is not as good as which is what we see right now? So some of these defense mechanisms will be discussed tomorrow, and we'll be looking at how the features changes if we apply those defense mechanisms and how the reconstruction changes in the similar way. Cool, I think that's it. So if there are any questions, let me know.
Great. Yeah, one question. Do you have any plans to release the, I know this is a tutorial, but the wider reconstruction test bed that you're having as some sort of a API or for other people to check their defense mechanisms against as baselines?
Yeah, I think that's very important for the community also. So yes, what we are working on right now is to basically develop a framework, and this framework will be accessible as an open source tool, and people can use different defenses, different attacks, and see what can be defended, what can be attacked, and basically we will have a benchmark. So if you are attending the talks, I had talked about during the Disco presentation, I had mentioned we are also releasing a benchmark data set. And what that benchmark data set is gonna consist of is multiple pairs of activations and images. And these activations and images will be used for different defense and attack mechanisms. And it will be more like a red hat, blue hat security game between two attacker and defender. And that way, I think it gives a level ground for benchmarking different algorithms and also establish some metric for information leakage.
Great. Yeah, there is a question. There are questions coming in on Slack now. So there is one from Francisca. Have you come across a good way to determine the best layer in the neural network to decide where you split it?
Yeah, I think it depends on multiple aspects. And in my view, there are three big pillars. So first big pillar is computation load on the client. So if we have a lot of layers on the client side, then you get a better reduction in information leakage. But at the same time, computation cost on the client increases a lot. So it really depends on computation on the client side. The other is basically how much information leakage you can afford. So again, this is intertwined with what we are considering as privacy here. And also, if your size of the information which you are communicating to the server is very low, then you get some communication advantage. So these are like some 2-3 pillars which are really computation, communication, then the utility you want and the privacy you want. And I think a good combination of these metrics would define which is the best split layer. And it would vary upon the use case because, for example, if it's a use case for IoT devices, then I think it makes more sense to go for, of course, it depends on the application, but it still depends. It would make more sense to have more computation load on the server. At the same time, if it's multiple hospitals collaborating together to learn, let's say, chest x-rays, then we might assume that they have some GPUs with them and hence they can run a good portion of the model by themselves. And
right. There's a question.
Maybe I can quickly show
sure
what I mean by different blocks. So yeah, you have to just see the traditional because the others are different methods. So here we start with the original image. After passing it through block 1, we can reconstruct the image well. After passing through block 2, block 3, and so on. The reconstruction of the image is still so well even till block 6, as you can see. And even at block 7, there is some information leakage in terms of reconstruction happening. And hence, that's why we need better mechanisms for defense, such that this information is gone. So yeah, this is for ResNet 18, which we were using in the tutorial also.
Great. There's more questions on Slack. Chandra Thapa is asking, is the current work on attacks limited to image data sets?
So in this tutorial, yes, and I feel a good portion of attacks, I mean, in the papers also focus for images because it's much more interpretable. The reconstruction attack is much more interpretable for images, but it's totally possible to reconstruct other modalities also, because as you can see, the architecture we use for adversary, so this adversary model, it could be anything. So as long as the access to Z and X data set is available, I think it should be possible to perform the attack. And of course, the information leakage or reconstruction quality could vary. For example, if it's a language model, then reconstructing the whole same language might lead to a different reconstruction result than what we expect on the images. But yeah, that's a definitely good direction to explore.
Great. So kind of an open-ended question. So I guess in the last 5 to 7 years with the GPUs, there was a race for better accuracies and better architectures in deep learning for high accuracy. But now privacy is becoming a very important research area. So do you see a similar race where people start putting more dollars and more GPUs for a race for performing reconstruction attacks? Or is there something else that you see as a future?
Yeah, so we actually see a lot of big architectures for generative modeling already. And some of these architectures are actually following exactly the same race, what you just said. So I think the privacy attack community can use those models. So for example, Big GAN basically showed that by adding more parameters and having a bigger architecture, you can generate images of much better quality. And similar idea has been adopted in variational autoencoder also, which is again can be used for generative modeling. So clearly that trend is already available in the generative modeling community and can be easily borrowed by privacy community as well. And by privacy, I mean this particular reconstruction of images.
Yeah, very cool. Let's see if there are more questions. Yeah, there is some on YouTube basically asking if the video recording would be available offline, which it will.
Guess so.
Yeah.
Yeah, maybe we should put the notebook link somewhere on YouTube, or I don't know.
Right. Yeah. Maybe overnight we can put it either on YouTube or on the website. We'll figure that out, or email to the registered participants in some form. Okay, this is fantastic. Yeah, this is great. So I think this officially concludes our first day of packed events and talks and tutorials. We're very glad that a lot of people have attended us. We hope to see all of you tomorrow again for the next set of talks, keynotes, and there's going to be another module of tutorial, which will be the module 3 for Code Your SL towards the end of the day. So we're going offline now. See you all tomorrow. Thank you.